Welcome to the Extraordinary 10 podcast, the place where the most magnificent and mind-bending facts in existence are explained to you in vivid detail.
Today we are embarking on a massive journey. We've researched 10 extraordinary facts about the Wood Wide Web, how trees talk to each other. We aren't just giving you a list. We are diving deep into the science, the mystery, and the why behind these wonders.
If you love exploring the unknown, don't forget to share this episode with a friend and subscribe to the channel. It's the best way to support the show and ensure you never miss a deep dive.
All right, are you ready to see the world differently? Let's start the clock. We're officially starting the clock. You might think you know the basics of this subject, but the reality is much bigger than you imagine. Let's start with the true scale. Fact number 10.
Okay, let's get into this. The Wood Wide Web. I mean, it's a great name, right? So catchy.
Oh, absolutely. He was on the cover of Nature magazine, back in the late 90s?
That's the one. But I feel like the pop science version of it kind of stops there. You know, it gets boiled down to trees are friends, which is fine, but it sounds like a kid's movie.
It does. It really simplifies what's going on. The actual biology suggests a system that's, well, it's a lot more complex and frankly more calculating.
Calculating, I like that.
Yeah.
So it's a critical distinction to make right from the start. That term, Wood Wide Web, it's useful, but maybe a little imperfect.
Yeah, exactly. Our internet, the one we're using right now, it moves data, information. This network, it moves physical matter.
Actual stuff.
Actual stuff. Carbon, nitrogen, water.
Yeah.
Along with the information. And it's not just, trees holding hands. It's a very specific anatomical fusion between two totally different kingdoms of life.
Plants and fungi.
Plants and fungi.
Right, and we should probably clarify what that fungus part actually is, because I think when people hear fungus, they picture a mushroom.
The thing you see on the forest floor.
Yeah, but that's just the tip of the iceberg, isn't it? The fruiting body. The real engine is all underground. It's the mycelium.
That's it, exactly. I mean, if you could peel back the top layer of soil, you'd see this vast, almost spider web-like network of what are called hyphae.
And these are microscopic threads.
Unbelievably fine. So delicate that, thousands of them could fit inside a single human hair. They just weave through everything, and their whole job is to connect.
Which is where that mycorrhizal relationship comes in. Myco for fungus, rhizal for root.
Right.
And these threads, they're not just loosely wrapped around the tree roots. In a lot of cases, they're actually physically going inside the root cells. It's a cellular handshake.
It is a total physiological integration.
Yeah.
The fungus becomes an extension of the tree's root system, but by orders of magnitude, it expands its reach enormously.
And what does the fungus get out of it?
Sugar. The tree does all the hard work of photosynthesis up in the sun, creating carbon, and it sends that down to feed the fungus, which can't make its own food.
And in return, the fungus is like this massive microscopic mining operation, scouring the soil for water, for nitrogen, phosphorus, and pumping it directly into the tree.
That's the classic symbiotic deal. You trade sugar for minerals. But fact number 10, the reason we're starting here is because it goes way beyond a simple one-to-one trade.
It's about the network between the trees. These fungal threads, they don't just serve one tree, they keep growing and connect to the next one and the one after that.
And suddenly you don't have a forest of individual competing trees. You have a circuit, a biological circuit.
That continuity, that's what changes everything, right? Because we used to see a forest as this, pure Darwinian battlefield.
Survival of the fittest. Big Douglas fir shades out a little sapling, the sapling dies, game over. The fir wins.
But the research, the stuff where they track isotopes moving through this network, it paints a completely different picture.
A contradictory one, yeah.
Yeah.
This gets us to that Robin Hood dynamic you hear about.
I do want to dig into that term a little. The idea is that the big dominant trees, the mother trees, they send their extra carbon to the little seedlings in the shade.
That's the mechanism.
Oh.
Suzanne Simard's work was the game changer here. She used radioactive carbon isotopes to literally trace the flow.
So she'd bag a tree, inject the isotope, and then just wait and see where it popped up.
Yep. And it didn't just stay in that one tree. It moved down into the mycelium, and then, sure enough, it appeared in the tissue of the neighboring trees.
And crucially, it moved from a source to a sink, from the tree that had a surplus to the ones that had a deficit.
Precisely. The trees out in the sun, making tons of sugar, were basically paying the bills for the little guys in the shade. Kept the understory alive.
Okay, here's my question, though. We call it Robin Hood, which sounds like charity, right? But what about the fungus? The fungus is the broker in all this.
Fungus.
Why would it move resources from a strong host to a weak one? I mean, that's not altruism, is it? It sounds more like portfolio management.
That is a brilliant way to put it.
Yeah.
You have to remember, the fungus needs the trees to survive. If it lets all the seedlings die off, it's losing future clients, future sources of sugar.
So by sharing the wealth,
It's diversifying its investments. It ensures the whole forest stays healthy, which in turn ensures its own long-term survival. It's a self-serving system that just happens to look cooperative.
and it stabilizes the whole ecosystem.
Yeah.
But it's not just food, is it? The network also carries warnings, defense signals.
Yes. Okay, so now we're moving from economics to information warfare.
Huh, I like it.
So when a tree gets attacked by, say, a bark beetle, its whole chemistry changes. It starts pumping out defense chemicals.
Right.
But what Simard and other researchers found is that this chemical panic doesn't stay local.
It broadcasts an alert.
It sends a signal out through the mycelial network. And we've measured this. Other trees, one that haven't been attacked yet but are on the same network, they start ramping up their own defenses preemptively.
So they're getting their chemical weapons ready before the enemy even arrives.
Exactly. They start making toxins, hardening their leaves. It's an immune response, but at the ecosystem level. Like herd immunity, but communicated in real time.
Wow. Okay, let's pause, because we're talking about invisible threads and underground chemistry, and it can all feel a bit abstract. I want to build that mental image for you, for the listener. The underground metropolis.
Let's do it. It's the only way to really get the scale.
Okay, so imagine we're shrinking down, not just small, I mean cellular level small. We're sinking down through the soil into that dark organic layer.
And visually, yeah, it would be pitch black. But if your senses could detect chemical signals and electrical pulses, it would look like a city at night. Sprawling. Neon.
You're at the base of a tree root and it's like a skyscraper wall. And coming out of it are millions of these glowing, translucent cables, the hyphae.
Some are thick, like fiber optic trunk lines, just pulsing with traffic. Water and nitrogen all rushing toward the tree.
And then branching off are these billions of tiny side streets, the little threads exploring every single nook and cranny. And you mentioned electrical pulses.
Correct. We've measured these spikes in electrical potential. They look a lot like the action potentials in our own nervous system.
So in this city, you'd see flashes of light zipping down the lines, little glowing packets of carbon leaving a big mother tree, navigating a junction, and being routed to a struggling sapling 50 feet away.
It is a living circuit board. The soil itself would be thick with messages. Just a constant chatter of molecular signals. I need phosphorus. Danger over here. Beetles detected.
And this is happening everywhere, all at once. The stats in our source material they're just staggering.
They really are. A single teaspoon of healthy forest soil can contain miles of these fungal threads.
Just let that sink in. 1 teaspoon, miles.
And if you take a single handful of that same soil, the number of fungal connections in it is greater than the number of stars in our entire Milky Way galaxy.
That's the one. That's the stat that always gets me. We look up at the night sky and feel insignificant, but there's a universe of equal complexity right under our feet.
Which is why the internet analogy, as good as it is actually an understatement. The internet has nodes and servers. This system's connectivity it's almost infinite. It's self-healing, self-organizing. It's been running for over 400 million years without a single reboot.
And unlike our internet, it fully integrates life and death. When a tree dies, it's not just logged off the network.
No, not at all.
Yeah.
It connects back to that superorganism idea. As a tree is dying, in its final moments, it does something amazing. It dumps all its remaining carbon back into the network.
It offloads its life savings.
It bequeaths its legacy to the community, yeah. The fungi act as executors, transporting those nutrients to the next generation. The substance of the ancestor literally becomes the body of the descendants.
Which is so different from how we think about agriculture, right? In a cornfield, you harvest the plant, you take it away, and the soil is left poorer. Here, the individual is just a temporary custodian of the network's wealth.
And this is why modern forestry is having a crisis of identity. For decades, the model was to clear-cut, remove all the competition to help your desired trees grow.
But when you do that, you're not just taking timber. You're destroying the whole infrastructure. You're ripping up the information superhighway.
You are. And if you specifically remove those big old mother trees, you're deleting the central hubs that hold the entire network together.
The living libraries.
That's a great term for it. They have the most connections. They hold the resources, maybe even the memory of past droughts or diseases. You take them out, and the resilience of the whole forest it plummets. The younger trees are suddenly on their own.
Which brings us to the big philosophical question here, the really deep part of the deep dive. We're using all this language, talking, deciding, warning, investing.
It's the big question, isn't it? If a system can sense its environment, process that information, communicate it, and then allocate resources for the good of the whole, is it thinking?
It's the architecture of a brain, just spread out underground instead of inside a skull.
We always define intelligence in our own image. Neurons, a central nervous system. But maybe intelligence is just an emergent property of any network that's complex enough. We're trying so hard to build artificial intelligence, these learning neural networks,
And there's been one under our feet the whole time.
since before the dinosaurs.
So ethically, what does that mean? When we clear-cut a forest, are we just harvesting timber, or are we dismantling a thinking ecosystem?
That's the ethical minefield. If it's just a warehouse of wood, it's an economic calculation. But if we start to see it as a community, with awareness, with agency, then our actions look very different. It's less like harvesting and more like lobotomy.
Dismantling a thinking ecosystem. That's a heavy thought. It suggests we're not just losing biodiversity, we're silencing a conversation that's been going on for hundreds of millions of years.
We're burning a library full of books written in a language we're only just now beginning to understand.
I think the biggest takeaway from Fact 10 is just humility. We thought we were the ones who invented networking. Turns out the trees had us beat by a few 100 million years.
And they built a better one. Sustainable, resilient, fully circular. We could learn a thing or two.
A fascinating place to start, just thinking that every time you walk in a park, this silent, massive conversation is happening right under your feet.
And we are only just learning how to listen.
That was Fact 10. Stay tuned. Fact 9 is coming up next.
Size and scale are just the beginning. As we move deeper into our list, the data starts to defy logic, moving right along to fact number 9.
And honestly, this is where we really have to ask you to suspend your disbelief for a moment, because the biology we're about to discuss, it starts to feel a little bit like magic.
Or like science fiction.
Or if you prefer a sci-fi angle, yeah, like extremely advanced alien technology.
I am fully ready for this. We are diving into the concept of the mother tree. Now, I have to admit, when I first saw this term in our research stacks, specifically for these massive old-growth forests, I got a little skeptical.
I can see why.
It sounds very poetic, like something from a fantasy novel or just a vague Mother Earth metaphor.
It does sound romantic, doesn't it? It evokes images of, I don't know, talking trees and Tolkien.
Exactly.
But here is the thing. In the context of modern forest ecology, mother tree isn't poetry. It is a rigorous scientific classification. It describes a biological reality that completely upends what we thought we knew.
Okay, so that is the mission for this deep dive then. We want to understand how a specific type of tree, a plant, let's just remember that, with no brain, no neurons.
No central nervous system.
Right, how it can orchestrate the survival of the entire forest around it. The research compares them to power grids, to internet service providers.
And even to family matriarchs. It's a multitasking feat that, frankly, puts most human logistics systems to shame.
So let's set the scene. If you walk into an old-growth forest, say the Pacific Northwest,
Or the ancient forests of British Columbia.
you see these massive ancient giants, and your instinct is to look up, right? You see the canopy, the height, the sheer dominance of the skyline.
Right, you see the dominant individuals, and for a long time, that's all science saw too. But the real story of the mother tree isn't happening in the sky. It's happening in the other direction.
It's happening underground.
It's happening underground.
Okay, so take us down there. What makes a mother tree different from just any other big tree? Is it just about its age?
Age is part of it, for sure, but it's really about connection. To understand a mother tree, you have to understand the infrastructure she presides over. And you have to understand that for, well, over a century, the prevailing dogma was all about competition.
Survival of the fittest.
Exactly. The Darwinian model applied to botany. We thought every tree was a solitary warrior, fighting its neighbors for every inch of soil, every drop of water.
Every ray of light.
Every single ray. It's a zero-sum game. If I get the sunlight, you don't. If I drink the water, you wither.
That was the model.
That was the model. But recent research, specifically looking at what we now call the Wood Wide Web, has it's dismantled that model. It turns out the forest isn't a collection of individuals, it's a system.
Okay, I see that term Wood Wide Web everywhere. It's catchy, but let's get technical for a second because I don't want to just gloss over that. What's the actual mechanism? It's not just roots touching, right?
No. I mean, direct root grafting does happen, but that's not the main event. The network is built on mycorrhizal fungi.
Okay, break that down.
Myco means fungus. Rhiza means root. So these are symbiotic fungi that colonize the root systems of trees.
Symbiotic. So there's a trade, a deal.
It's the oldest trade deal in nature. Think of the mushroom you see on the forest floor as just the tip of the iceberg, the fruit. Underground, that fungus is a vast network of tiny threads. It's called mycelium.
And the fungus can't photosynthesize.
Exactly. It lives in the dark, it needs sugar, it's hungry for carbon. The tree, on the other hand, is a sugar factory, way up in the sky, so they strike a bargain.
What's the bargain?
The fungus gives the tree hard-to-get soil nutrients, like phosphorus and nitrogen, and it massively expands the tree's water absorption capacity. We're talking sometimes by 1,000 times.
1,000 times. Wow. Okay, so the fungus is like an extended root system for the tree.
Correct. And in exchange, the tree pays the fungus in sugar liquid carbon dripped directly into the fungal network.
So far, that sounds like a private transaction. One tree, one fungus.
And that's what we thought for years. But here is the breakthrough. We found that these fungal threads, the mycelium, they don't just stop at one tree. They keep growing. They connect to the roots of a second tree, and a third, and a fourth.
So they are literally wired together.
Literally wired. We are talking about fungal threads so fine they can slip through the eye of a needle, creating a physical bridge between trees.
And this brings us to the pivotal work of Dr. Suzanne Simard. She's the heavyweight in this field, isn't she?
She is the one who really blew the lid off this in the 1990s. And she didn't just speculate, she proved it. She used radioactive isotopes to track the movement.
Walk us through that experiment, because that sounds like the smoking gun.
It is. She went into the forest, covered trees with plastic bags, and then tagged carbon-13 and carbon-14 into the bags.
So the trees would breathe it in.
Right. They absorbed it, turned it into sugar. Then she used Geiger counters to trace where that sugar actually went.
And it didn't stay in the tree.
It did not. The isotopes traveled down the trunk, into the roots, through the fungal network, and she found them in the tissues of neighboring trees. She could literally measure the flow.
They aren't just competing, they are sharing.
They're sharing, and this is where the mother tree concept becomes crucial. Dr. Simard found that the biggest, oldest trees in the forest, these mother trees, they're the hubs. They're the most heavily connected nodes in the entire network.
So one mother tree can be connected to how many others?
Hundreds. A single mother tree can be connected to hundreds of other trees.
Okay, so the connection is real. But I have to play devil's advocate here. Evolution is usually pretty ruthless. Why would a tree give away its resources? If I'm a big, successful Douglas fir, I've won the game. Why am I shipping my hard-earned sugar to the little guy next door?
That is the million-dollar question. And to answer it, you have to look at the environment of the forest floor. It's dark down there. In an old-growth forest, the canopy is so thick that very little sunlight actually hits the ground.
Right. It's deep shade.
So if you are a young sapling, a seedling, you physically cannot photosynthesize enough to keep yourself alive. You are running a calorie deficit. By all the standard rules, you should die.
Starving for light.
Exactly, but in these forests, the seedlings don't die, they just wait. And the reason they don't die is that the mother tree, that giant looming above them, is redirecting her own liquid carbon down through the network.
And pumping it directly into them.
She's pumping it directly into the systems of the seedlings. She's subsidizing them, keeping them on life support until a gap opens in the canopy and they can finally reach the light themselves.
It's a remarkable act of ecological generosity.
Yeah.
But does she do this for everyone? Is she just a universal donor, feeding any random shrub that pops up?
And this is where the science gets truly mind-bending. And it's where we have to be careful not to, anthropomorphize too much, but the data is the data.
What does the data show?
The research shows that mother trees can distinguish their own kin from strangers.
Wait, hang on. They know who their kids are? How? I mean, they don't have eyes, they don't have DNA tests.
It's all chemical. They use chemical signaling in the soil. We believe it involves specific root exudates chemical markers that identify genetic lineage. When a mother tree's roots encounter the roots of her own offspring, the interaction changes.
Changes how?
She favors them. When researchers tracked that isotope flow, they found the mother tree sends significantly more carbon to her own seedlings than to stranger seedlings growing right next to them.
That's incredible.
And she also reduces the competitive spread of her own roots to give her offspring more physical room to grow.
That sounds suspiciously like parenting.
It mirrors what biologists call kin selection in animals. We accept that a lioness cares for her cubs, or humans care for their children. But to see a plant making strategic, supportive decisions to ensure the survival of its specific family line, that challenges everything.
It implies a long-term strategy. It's investing.
Exactly. They aren't passive scenery, they are active participants.
It really changes your perspective when you walk through the woods. You're not in a factory of wood, you're in a nursery.
Or a family reunion where the grandmother is cooking dinner for everyone and making sure the grandkids get the biggest portions.
I love that. But I want to try and visualize the scale of this because I think it's easy to underestimate what's happening. The sources suggest a thought experiment.
Yes, let's do it.
Okay, so, listener, I want you to picture this. You are standing at the base of a Douglas fir, a 400-year-old Douglas fir.
This tree was a sapling when Galileo was looking at the stars.
Right, 400 years. You try to hug it, but your arms can't even span a quarter of the trunk. It's massive.
Now, imagine you have X-ray vision. You can look down through the soil, directly beneath your feet. What you would see isn't just a few big roots. You would see something that looks like a metropolitan transportation hub at rush hour.
A subway map of biology.
It really is.
Yeah.
You have the mother tree's primary roots, massive anchors as thick as your torso. But branching off those are millions of finer roots, and off of those are the fungal threads.
And that's the network.
Yes. In a single pinch of soil, there can be miles of these fungal threads, extending outward, connecting that one mother tree to hundreds of others.
It's a dense web.
And if you could zoom in to the molecular level, you'd see the flow. It would look like blood flowing through capillaries. Molecules of carbon, nitrogen, water, all streaming from the mother tree into the fungal highway, rushing toward those struggling saplings.
And you mentioned water, too. It's not just food.
Crucially, yes. Think about a drought. When the topsoil dries out, the shallow-rooted young trees are in immediate danger. But the mother tree, her roots go deep. She can tap into aquifers no one else can reach.
So she acts as a hydraulic pump.
She pulls the water up from the deep earth and then redistributes it horizontally through the network to the neighbors who are dying of thirst.
That's actually heroic behavior from a tree. It's not, I have water, I'm good. It's, we need water.
And it extends to defense. The sources mention that if a neighbor is attacked, say by an insect, that neighbor sends a chemical distress signal through the network.
A warning.
A warning. The mother tree receives that signal and primes her own defenses. She starts producing chemical repellents before the bugs even arrive at her trunk.
She's listening to the police scanner and locking the door.
That is a perfect analogy. And she can warn the rest of the family, too.
Okay, I have to bring up my absolute favorite fact from this entire deep dive. We've talked about the what and the how, but we need to talk about the how much. Because when I hear sharing sugar, I think of a teaspoon here and there.
It is definitely not a teaspoon.
The statistic in the source blew my mind. A single mother tree, in a single growing season, can transfer enough carbon to the network to equal the weight of a full-grown grizzly bear.
It's a staggering amount of mass.
A grizzly bear, that's what, 400 to 600 pounds?
Easily. Imagine moving 600 pounds of physical material molecule by molecule through microscopic threads underground. It is an industrial-scale operation.
And that really emphasizes the cost to her, doesn't it? This isn't just extra stuff. To move that much carbon means she is prioritizing the community's survival, maybe at the cost of her own growth.
Precisely. In biological terms, it's an immense energy expenditure. She's investing heavily in the next generation. It really reinforces that idea of the mother. It's a sacrificial act, in a way.
So we have this biological entity that is feeding the kids, watering the neighbors, and listening for burglars. The source uses an analogy here that I think helps. It compares her to a power plant.
Yes, but a very smart power plant. Imagine a power plant supplying electricity to a neighborhood. But instead of just blindly sending power down the lines, it was actively monitoring the status of every single house.
Oh, House A is having a blackout. Send more juice.
Exactly. House B is dealing with a heat wave. They need more support. And House C is my daughter. I'm going to make sure she stays online no matter what. It's doing all of this dynamic rerouting in real time.
And this is the part that gets me. She is doing all of this complex management while physically holding up a hillside and a canopy hundreds of feet in the air.
It is a level of biological complexity that we are only just beginning to map out.
Which brings us to the heavy part of this conversation, because once you understand this, you look at a logging truck very differently.
You do, and this is the ecological tragedy embedded in our modern forestry practices.
The source points out that in standard forestry, the target is usually the biggest, oldest trees. They have the most wood. They're the most valuable.
Economically, yes. If you view a forest as a warehouse of timber, you take the biggest inventory first. It's called high grading. But ecologically, when you cut down a mother tree, you aren't just harvesting wood.
You're cutting the main server.
You are dismantling the hub. You are dismantling the memory banks and the communication centers. The source uses a very poignant analogy. It says cutting down the mother trees is the ecological equivalent of removing all the elders from a village.
That paints such a stark picture.
Imagine a village where you take away the grandmothers and grandfathers, the ones who know where the water is, the ones who know how to survive a harsh winter. You take them away, and then you wonder why the village collapses.
And that's what we're seeing in the data, isn't it? It's not just that the big trees are gone, the little ones start dying too.
Absolutely. We used to think, oh, if we cut down the big tree, it opens up the canopy and gives the little ones more light.
Sounds logical on paper.
But in practice, without the mother trees to pump nutrients and water to them, the survival rate of the young trees just plummets. The nutrient circulation stops, biodiversity declines. You might replant trees, but without the parents there to hook them into the network, they are just isolated sticks in the ground.
It's heartbreaking. It really shifts the definition of a forest from a collection of trees to a community.
And that leads to the philosophical shift this research demands. We have to redefine what we mean by intelligence in nature.
Right. We usually think of intelligence as having a brain. If it doesn't have a brain, it's just a vegetable.
But here we have communication, empathy, care, long-term planning, all woven into the biological fabric of the forest. It suggests that strength in nature isn't about isolation.
It's about connection.
Strength is connection. The forest survives because it is connected. The mother tree is proof that evolution favors cooperation just as much as competition.
It forces us to confront that uncomfortable truth the source mentioned. Can we afford to keep treating these beings as mere resources?
That is the ultimate question. We call them natural resources, implying they're just stuff for us to use. But if a mother tree is an irreplaceable architect of life, as the source puts it, do we have the right to cut her down?
Especially now.
Especially now, with climate change accelerating, we are destroying the very family structures that hold the ecosystem together right when we need them the most. We are dismantling the support system.
The forest is not a collection of individuals. It is a community reliant on its elders. And we are systematically removing those elders.
And we do so at our own peril.
So here is a thought to leave you with. We spend a lot of time worrying about our own legacy, what we leave behind for our kids. But deep in the forest, there is a legacy being passed down right now through fungal wires in the dark, from a 400-year-old giant to a tiny sapling, a legacy of carbon, of water, of protection. It makes you wonder, if a tree can prioritize the next generation over its own immediate growth, why do we humans find it so hard to do the same?
That is the question.
That covers 9. Ready for the next one? Let's head to Fact 8.
To sustain the wonders we've just described, there has to be a relentless high-speed system working behind the scenes. Let's look at the fact number 8.
For this deep dive, we're actually going to leave the damp forest floor behind. I want to take you somewhere completely different.
Okay, where are we headed?
We're heading thousands of miles away to the African savanna. It's a totally different landscape with a different set of rules.
All right, I can picture it. I'm imagining that, that heat shimmer off the ground, the golden grass, and those classic flat-top trees, the acacias.
That's our protagonist, the
Yeah.
acacia. So zoom in on one of those trees and picture a giraffe walking up to it.
Okay.
To anyone just, watching on safari, this looks like the most peaceful scene you could imagine. The giraffe reaches out with that long tongue and just takes a bite.
Right, it's the classic circle of life moment we see in documentaries. Herbivore eats a plant, everybody's happy.
Except maybe the plant. But we tend to assume plants don't really have an opinion on the matter.
Yeah, we think of them as just salad bars with roots, basically.
And that is the exact assumption we need to just dismantle right now.
Yeah.
Because if we could switch our view, if we could see things on a molecular level.
Or see chemical signals like colored.
Exactly. Then that so-called peaceful lunch would look like, well, a battlefield.
A battlefield? I mean, that sounds a little dramatic for a tree, doesn't it? It has thorns, sure. But once the giraffe gets past those, isn't the fight over?
The thorns are just the outer walls of the castle. The real war, the high-tech chemical war that starts after the bite.
After the bite.
That crunching sound isn't just a snack, it's a trigger. It sets off one of the most sophisticated high-speed defense networks in all of biology.
Okay, you have my full attention. So we're talking about a tree fighting back, but
Yeah.
It can't move. It has no brain, no muscles. How does it fight a 2-ton animal?
It all starts with the chemistry of that bite. When a giraffe tears a leaf, it's not just physical damage. The animal's saliva mixes with the plant's torn tissue.
And the tree knows the difference.
It registers that specific injury immediately. We're not talking about a slow reaction here. Within seconds, the acacia starts producing and releasing a gas, a volatile gas called ethylene.
Ethylene. I think I know that one. Isn't that a plant hormone? The one that makes fruit ripen?
It's the exact same chemical, C2H4. But the context is everything. Here, the acacia isn't trying to ripen an avocado, it's weaponizing it.
As what?
A warning.
As a distress beacon. Think of it less like a hormone and more like an invisible smoke signal. And because it's such a tiny, light molecule, it just billows out from the damaged leaves and drifts on the wind.
So wait, I want to clarify something. We've talked before about the wood wide web, right? The fungal networks underground, but that's like a hardline connection. This is wireless.
This is completely wireless, airborne messaging. And there's a really good reason for that. Those fungal networks are amazing, but they're relatively slow.
You don't have time for that.
You don't. If a giraffe is eating you right now, you can't wait to send a message down through the roots. You have to broadcast. Speed is everything. Okay, so this gas cloud wafts out. It hits the other trees nearby, the ones 50 feet away that haven't even been touched yet. What happens then?
This is where the system gets so intelligent. Those neighboring trees have receptor sites on their leaves. They basically taste or smell that ethylene in the air.
So they get the message, emergency at sector 7.
And they don't hesitate. The second they detect that ethylene, their own metabolism goes into overdrive. They start pumping their own leaves full of tannins.
Tannins, another one I know from wine. It gives red wine that dry feeling in your mouth.
It does, but the dose makes the poison. In a good wine, you have a nice balanced amount of tannins. The acacia isn't making wine. It's flooding its system to toxic levels.
So if I'm the giraffe, and I finish with the first tree and wander over to the next one, which looks totally fine, what happens when I take a bite?
The experience would be shocking. The source material describes it like biting into an unripe persimmon, but then multiplied by 10.
Wow.
It's a violent astringency. The tannins bind to all the proteins in the giraffe's saliva in its digestive tract, and they make the leaves completely inedible.
So it's not just a bad taste, it basically turns the food into poison.
It can actually stop the animal from digesting protein at all. If it kept eating, it could literally starve with a full stomach. So the giraffe takes one bite, realizes a whole salad bar has gone bad, and it has to move on.
But giraffes can't be that dumb, right? This is an evolutionary arms race. They must have a counter strategy.
You are absolutely spot on, they do. Giraffes have learned a couple of things. First, they only browse for a short time at any one tree. They try to eat and run before the chemicals really build up.
Get ahead of the production line.
Exactly. But the second strategy is the brilliant one. It has to do with how the signal travels.
Let me guess. It's in the air, so the giraffe moves upwind.
That's it. A giraffe will almost always browse into the wind. If the wind is blowing from the north, the giraffe walks north to the next tree.
Because the chemical smoke signal is blowing behind it. The trees up ahead haven't gotten the warning call yet.
It's this incredible high-stakes game of tag, the giraffe trying to outrun a gas cloud. But even with that strategy, a giraffe can rarely feed on one grove for long. The entire area can go from vulnerable to fully defended in, 5 to 10 minutes?
That speed, that's what really messes with my perception of plants. We have this plant blindness. We assume they work on a geological timescale.
Right. I'll grow a new leaf over the next few weeks.
But this is a real-time metabolic response. It's behavior.
It absolutely is behavior. We think behavior means movement, like a gazelle running away. But for a plant, rapid chemistry is its behavior.
I have an analogy for this to kind of lock it in. It reminds me of a smart city concept.
Oh, interesting. How do you mean?
Well, think of a city where every building is connected, but there's no central command.
Okay, a decentralized grid.
Exactly. So a burglar breaks a window at one house. That house doesn't just call the police. It instantly blasts a Wi-Fi signal to the entire neighborhood.
And the other houses, they don't need to wait for instructions.
No. There's no mayor of the block thinking about it. They get the signal and boom, deadbolts lock, steel shutters roll down, floodlights come on. The house next door is a fortress before the burglar even gets there.
That is a perfect comparison. And think about how our emergency services work. You call 911 and you're hitting a central hub. An operator takes the call, dispatches a unit.
There's so many steps, so many points of failure. It takes minutes.
The Acacia system has zero bureaucracy. It's a distributed network that achieves a coordinated, grove-wide defense without a single neuron or a brain to command it. It's just elegant chemistry.
And it gets even more elegant, right? Because we've been talking about defense, putting up shields, but some plants go on the offensive. They call for backup.
They hire mercenaries, yes.
Mm.
This is where we get into what are called tritrophic interactions. 3 levels of the food chain, all in one chemical conversation.
So walk me through that. A caterpillar starts chewing on a leaf. The plant sends out a signal. But it's not just a generic help, is it?
No, and this is the detail that just floors me. The plant can actually analyze the saliva of the specific caterpillar eating it.
You can tell what species it is.
It identifies the species, and then it creates a very specific cocktail of chemicals, VOCs, that are designed to attract the exact predator of that caterpillar.
That's wild. So it's not calling 911, it's calling a very specific hitman, like, I've got a problem with this specific guy, send the parasitic wasp that preys on him.
That is literally what happens. The wasps pick up on that unique scent trail, use it like a homing beacon, fly straight to the plant, and lay their eggs inside the caterpillars. The plant gets saved.
The enemy of my enemy is my friend, and the tree is the one brokering the deal.
Exactly. It's a diplomatic landscape. The forest isn't just a bunch of passive objects, it's a constant, invisible symphony of signals, warnings, alliances, deceptions. The forest is watching and listening and deciding, just with molecules.
That brings the question of cost, though. If these tannins and VOCs are so effective, why not just be full of them all the time? Why wait for the bite?
Because it's expensive, metabolically expensive. Making all these complex chemicals takes a huge amount of energy.
Energy that could be used for growing taller or making seeds.
Right. If a tree was in lockdown mode all the time, it would get outcompeted. It would lose the race for sunlight. It's a balancing act.
A budget. You can't spend everything on defense or your economy collapses.
Which is why listening is so important. You only deploy the expensive weapons when you know the threat is real.
This is leading us to a philosophical question, I think. We've just described a system that perceives a threat, communicates it, strategizes, recruits allies, manages resources.
It sounds a lot like we're describing a conscious being.
Exactly. But I'm looking at a tree, I know it doesn't have a brain, no neurons, so can we really call this intelligence? Or are we just, projecting?
And that's the debate that's really shaking up biology right now. Our traditional definition of intelligence is tied to hardware. You need a brain, a central nervous system.
Input, brain processing, output.
But the acacia shows us distributed intelligence. Or you could call it swarm intelligence. It solves a very complex problem, how to not get eaten, using a decentralized network. Does it matter that the processing didn't happen in one lump of gray matter?
If it works, it works. It's a functional intelligence.
And this system has been running for hundreds of millions of years. It's been around far longer than brains have. We think of our brain as the pinnacle, the only real way to process information.
But maybe it's just one solution, a very high energy, very fast solution, but not the only one.
Precisely. And this ties directly into our own technology, into artificial intelligence.
I was just thinking that. We're so focused on building AI that works like a human brain. Neural networks, centralized servers.
But there's this whole other field of AI research looking at swarm intelligence.
Yeah.
Inspired by ant colonies, by plant networks.
Mm-hmm.
If you want to build a fleet of drones to explore Mars, you don't want one giant central brain that could fail.
You want every drone to be able to talk to its neighbor. You want the acacia model.
So the future of AI might actually look a lot more like an ancient forest than we think. We're trying to build in silicon what nature perfected in cellulose millions of years ago.
That really flips the script. We see plants as these lower life forms, but maybe they're running a kind of software we're only just beginning to grasp.
And that's the thought I hope people sit with. We miss so much of what's happening around us because it doesn't operate on our frequency. We can't smell the ethylene. We don't see the world in that way.
It's an illusion created by our own senses. We assume the room is quiet just because we can't hear the conversation.
The forest is never quiet. It is a roaring marketplace of information. We just need to learn how to tune in.
I feel like the next time I walk in a park, I'm going to be looking over my shoulder, wondering if the trees are gossiping about me.
Well, the grass actually does release a distress signal when it's cut. That smell of freshly cut grass, that's basically a chemical scream.
Oh, that's great. So the smell of summer is actually the smell of widespread panic. Thanks for that.
Science isn't always comforting, but it always makes the world more interesting.
It certainly does. It's humbling, really. We think we're masters of communication with our satellites and fiber optics.
And the trees beat us to it by a few 100 million years. And they power their network with sunlight and water.
So to wrap this up, when you look at an acacia or any tree, what are you really looking at?
You're looking at a fortress, you're looking at a mobile chemical factory, and you're looking at a single node in a vast, ancient, and invisible communication network.
A veteran of a silent war that, weirdly, is the only thing that actually maintains the peace.
That's the beautiful irony of it. If the trees didn't fight back, the giraffes would eat everything, and then they would starve. The conflict creates the balance.
A perfect stalemate. Well, my view of a simple tree has been officially and permanently altered. I think I'm going to go have a salad now, but I might apologize to it first.
Just chew quickly.
Will do. This was fascinating. Thanks for guiding us through that invisible battlefield.
My pleasure.
That covers 8. Ready for the next one? Let's head to fact 7.
Welcome back. We're diving into a hidden architecture that most people never even realize exists. This is fact number 7.
It is. And honestly, this one, it kind of reframes the way I look at an entire forest. We are talking about a concept called the memory of thirst.
The memory of thirst. That sounds so poetic, doesn't it? Almost like a novel.
It does.
But we aren't here for poetry today. We're here for hard biology. And specifically, we're tackling this idea that I think most of us have, that nature is, resilient in this very bouncy kind of way.
Right, the rubber band theory of nature.
Exactly. The logic goes,
Yeah.
you have a drought, it's a crisis, trees look awful.
Everything looks bleak.
Right. But then the rains return, everything turns green again, and we just think, okay, crisis over, back to normal. We assume the slate has been wiped clean.
And that assumption is precisely where the new science, especially these 2025, 2026 studies on poplar trees, just stops us in our tracks. The research is suggesting that the slate is not wiped clean.
So the trees don't forget.
They don't forget. They hold on to that experience, that thirst, for years sometimes, and it physically changes them.
Okay, so when we say memory, are we being a little metaphorical here?
Yeah.
Like a piece of metal remembers its shape? Or is it something more?
It's much more. We're talking about biological learning. It's not cognitive. I mean, obviously there's no brain involved, but it is a functional memory. The tree is basically saying, okay, I see what happened there, and I'm going to rewire my biology so it doesn't hurt as much next time.
That's the hurdle I want to clear right away, because I think a lot of people will get stuck on the mechanics. To remember something, you need neurons, a brain somewhere to store the data. A tree is. It's wood and leaves. Where is it filing away the memory of a drought from last year?
That is the central question. If you don't have a neural network, where do you put the data? And the answer is in this field that has it's absolutely exploded in the last few years. Epigenetics.
Okay, epigenetics. We hear that word a lot, usually with human health and lifestyle, but break it down for a tree.
Okay, so the best way to think about it is that the tree's DNA is like a huge instruction manual. It's a big, hardbound book.
And the text in that book, the genetic code, that's fixed.
It's fixed. You can't rewrite the book in the middle of a drought. That would be evolution, and that's a really slow process.
Takes thousands of years. Right.
Exactly. Evolution is a slow writer. But what you can do is you can annotate the book. You can take a highlighter or a sticky note and you can mark up specific pages. That's epigenetics. It's that layer of information on top of the DNA that tells the cell which parts of the manual to read and which parts to ignore.
So the text is the same, but the emphasis changes.
Precisely. In the case of these poplar trees, when that drought stress hits, the cells start attaching these little chemical tags to the DNA. The process is called DNA methylation. You should think of them as molecular sticky notes.
I love that analogy from the source material. It makes it really tangible. So a drought hits, the tree is losing water, and it basically goes into its own DNA library with a pad of Post-its.
It really does. It starts slapping these little notes on genes that control things like water conservation, root growth, or when its pores open and close. And the note basically says, urgent, read this part first, don't ignore this.
And the critical part here is that the sticky notes don't just fall off when the rain comes back.
That is the memory. Even when the soil is wet again and the pressure is off, those methyl groups, those sticky notes, they stay attached. The tree is now chemically feder. Scarred is one word, but maybe annotated is better. It's biologically different. It's primed to read its own instruction manual differently from now on.
So where does this happen, physically? In the tree? Is it in the leaves? Because leaves fall off in the autumn. The memory would just be gone by spring.
That's a fantastic point, and it's why the location is so important. It happens in the cambium.
Okay, that's the layer just under the bark. The bright green skin you see if you scratch a twig.
Exactly that. The cambium is the factory floor. It's the generative tissue that makes all the new wood and all the new bark. By putting these epigenetic markers in the cambium, the tree makes sure that every single new cell it creates from that point on carries the memory.
So it's not just patching up old damage.
No, it's building the future tree based on the trauma of the past. It is hard-coding the lesson into its permanent structure.
Okay, so let's make this practical. We have a tree with these sticky notes all over its DNA. It's been through a tough time. If I'm walking in a forest and I look at this tree next to a, let's say, naive tree, one that's had plenty of water his whole life, what's the actual difference? How does this memory show up in the real world?
It all comes down to speed and structure. The remembering tree is no longer an optimist.
Right. The naive tree is just assuming water will always be there. The remembering tree is a realist.
Or a survivalist. The moment the environment even starts to get a little bit dry again, that remembering tree reacts aggressively. First, you'd see it in the stomata.
The little breathing pores on the leaves.
Right. Those are the windows the tree opens to get CO2 for food. But when they're open, water escapes. It's a dangerous trade-off.
A balancing act.
It is. And a naive tree keeps its windows open as long as possible. It's greedy for growth. A remembering tree slams those windows shut at the first sign of trouble. It will choose to save water over eating CO2 immediately.
So it goes into a kind of lockdown. It would rather starve a bit than risk dehydration.
Instantly. And it goes even deeper than that. The internal plumbing, the hydraulic architecture inside the trunk, it actually changes. The tree adjusts the width of its water-carrying vessels.
And why does that matter? The width of the pipe.
It matters because of air bubbles. When a tree is under drought stress, the tension on the water inside can get so high that the water column can just snap. It creates an air bubble, an embolism.
And that blocks the pipe.
Blocks it dead. Too many of those, and the tree dies. So a remembering tree builds narrower vessels that are much harder to break. It makes the plumbing safer, even if it's a bit slower.
And what about underground, the roots?
Oh, that's often where the most dramatic changes. A naive tree might have shallow, spreading roots to grab easy nutrients. A remembering tree will often start sending roots much deeper, or it'll change its root hairs to pull moisture from tighter soil. It stops focusing on growing tall and starts focusing on fortifying its position.
It sounds like it's reallocating its budget. Less on expansion, more on defense.
That is the perfect way to put it. Which brings us to that city infrastructure analogy we were talking about. I think it really helps frame the scale of this.
Yeah, I found this really helpful. It moves you away from thinking about the tree as just one thing.
Exactly. You see it as a system.
So the idea is you have a city that gets hit by some disaster, like the water supply just fails completely.
Reservoirs run dry, total crisis.
But eventually the crisis passes, the water comes back. Now, in the old reset view of nature, the city would just, fix the broken pipes and go back to business as usual.
Everyone just forgets it happened.
Right. But the memory of thirst idea says, no, that is not what happens. The city doesn't just fix the pipes. It convenes a council, it rewrites the laws.
It installs smart meters everywhere. It passes rules that say, the moment our reservoir drops by 1%, automatic rationing kicks in. It fundamentally changes its own blueprint.
So the next time a dry spell comes along, the neighboring city, the naive one, it panics and collapses. But the remembering city barely blinks. It just switches to its new protocol. It's been hardened.
And that is exactly what the tree is doing. And this creates this fascinating trade-off, right? The tree that has never suffered, the one in the perfect spot, is actually at a disadvantage in a changing climate. It's soft.
So this really flips our idea of a healthy tree on its head.
Yeah.
We think the biggest, fastest growing tree is the winner, but you're saying in a volatile world, the scruffy survivor might be the superior biological machine.
In the long run, absolutely. Resilience often comes at the cost of rapid growth. You can't spend all your energy on deep roots and also grow 10 feet a year. But when a drought is coming, you want to be the one with the deep roots.
How long does this memory even last? I mean, were we talking a summer, a year, decades?
Well, the research confirms it's definitely transannual. So if you stress a tree in year 1, let it rest over the winter, and then stress it again in year 2, it still remembers what happened in year 1.
So it doesn't just wake up in the spring with a blank slate?
No. And we're still figuring out the upper limits, but the mechanism is just so similar to our own immune system.
Okay, connect those dots for me. A tree coping with thirst and me fighting off the flu.
Well, think about when you get a virus. You fight it, you recover, you feel back to normal. But you're not, really. Your body has created memory B cells and T cells. It keeps a molecular mugshot of that pathogen.
So if I encounter that same virus 5 years later,
Your body recognizes it instantly. It mounts a defense that's faster and stronger than the first time. You might not even get sick. The tree is doing the same thing, but its enemy isn't a germ. It's the physics of water potential. It's using past trauma to ensure future survival.
Okay, this is all incredible for a single tree. But the source material throws a curveball that I have to say I found genuinely hard to believe. It mentions transgenerational memory.
This is the twist. This is what's really shaking up botany and, frankly, evolutionary biology.
Are we actually saying a parent tree can pass these sticky notes down to its kids?
Yes, the evidence is pointing that way, that these epigenetic marks, these instructions for handling drought, they can be passed into the seeds.
Hold on, because that sounds almost anti-Darwinian.
Yeah.
You inherit DNA, not experiences. If I lift weights my whole life, my baby isn't born with big muscles.
Correct, and that was the old argument. But epigenetics blurs that line. The tree isn't changing the DNA sequence, it's passing down the annotations. It's giving its offspring the manual, but with the drought survival chapter already highlighted and bookmarked.
So a seedling, one that's never felt a dry day in its life, could start growing already prepared for a drought, just because its mother went through one 10 years ago.
That is exactly what the data implies. It's ancestral knowledge. The seedling essentially knows the world is dangerous before it even breaks the soil.
That's incredible.
Heh.
So why is this so important right now? Why have this shortcut?
Speed. It's all about speed. Genetic evolution, random mutation and selection, it's incredibly slow. It takes thousands of years for a population to adapt.
And our climate is not waiting thousands of years.
Not at all. If trees had to wait for random genetics to make them drought resistant, entire forests would be gone before they could adapt. Epigenetics lets them adjust within a single lifetime and then warn the next generation. It's a rapid response system.
This has to have huge implications for how we manage forests. If we know this, we should be using it.
We can, absolutely. And this is where we get into the practical side. We're looking at something you could call forestry boot camp.
Forestry boot camp. Okay, I'm picturing a tiny drill sergeant yelling at saplings.
It's not far off in a biochemical sense. Think about how we do reforestation now. We grow seedlings in these perfect nurseries, perfect soil, perfect water, everything.
We coddle them.
We raise them to be naive. They have no sticky notes. Then we take these pampered saplings and plant them on a dry, exposed hillside and wonder why so many of them die.
They get hit by reality and they just don't know what to do.
They panic. They don't have the protocols. So the boot camp idea is to deliberately prime them. We expose them to mild drought stress while they're still in the nursery.
Just enough to scare them a little bit.
Just enough to get them to start writing those sticky notes in their cambium. You stress them, let them recover, stress them again, then you plant them. You're sending them out into the world with a toolkit already installed.
You're basically inoculating them against the future.
Exactly. We're not just planting genetics anymore, we are cultivating experience.
This is fascinating, but also casts a pretty dark shadow on deforestation. The source material brings up this philosophical angle, and I found this part really haunting.
It is the most troubling part of all this, I think.
It's this idea of the living library. If an old tree, a 500-year-old oak, say, has been accumulating these sticky notes for centuries, it's a repository of local knowledge.
Exactly. It has learned the specific pests, the wind patterns, the drought cycles of that one valley for 500 years. That information is physically encoded in its body.
So when we clear-cut an old-growth forest, we are not just harvesting timber. We are burning the library.
We're deleting the operating system. We're erasing centuries of hard-won data.
And when we come back to replant, even with the same species, those new trees are blank slates.
They are rookies. And that's the restoration dilemma. We are rushing to plant billions of trees, which is great, but we're often replacing a team of veteran survival experts with a bunch of fresh recruits.
Recruits who don't have that institutional memory.
And in a climate this volatile, that memory can be the difference between life and death. A naive forest might collapse in a heat wave that an experienced one would have survived.
It makes you value old-growth forests differently.
Yeah.
Not just because they're beautiful or rare, but because they are smart.
You're wise, and that wisdom is physical. The source used a phrase I just can't get out of my head, the chemical scars of survival.
The chemical scars of survival. That's powerful. It's just that the damage we see on an old tree, the gnarly bark, the twisted branches, that's not a sign of failure.
No, it's a record of battles won. It's intelligence, and it tells us we need to be really humble about thinking we can just rebuild nature. You can plant a tree, but you can't plant a memory. That takes time.
So practically, where does this leave us? What's the takeaway when you look out at the woods?
I think it leaves us with a responsibility to change our philosophy. We need to stop seeing forests as just collections of timber units and start seeing them as complex learning societies.
So, less clear-cutting.
And more respect for that continuity of knowledge. Maybe it means we leave more of the old mother trees, the ones with the deep memory banks, so they can pass that epigenetic information down to the seedlings growing around them.
We have to keep the teachers in the classroom.
That's it, perfectly put. You fire all the teachers, the school falls apart. We have to preserve the wisdom, not just the wood. We're gonna need trees that know what they're doing.
It's a humbling thought. We walk past them every day thinking they're just background scenery. But they're standing there silently remembering battles that happened before we were even born.
And they're actively preparing their children to fight those battles all over again.
Well, next time I see a gnarled old tree, I'm gonna look at it with a lot more respect. It's not just old, it's educated.
It's a survivor. And it has the notes to prove it.
That covers 7. Ready for the next one? Let's head to fact 6.
We've looked at the map. Now let's look at the engine's power source. This next revelation sounds more like science fiction than reality. Shifting gears to fact number 6.
It really does. I mean, it sounds like something straight out of sci-fi because it completely challenges this idea we all have about nature.
The idea that it's quiet.
Exactly. That plants are silent.
Right, because that's why you go to a forest. I mean, I know I do. You go there for the quiet, for the stillness. You think of trees as these, stoic, silent objects.
Passive.
Yeah.
That's the word we always use. We see them as like furniture for the landscape. But fact 6 just flips that whole idea on its head. It turns out trees aren't silent at all. They're actually incredibly noisy. And under certain conditions, well, you could say they're screaming.
Okay, but you're not talking about like the wind in the leaves or wood creaking.
No. This is a sound the tree itself is generating. It's a biological sound. Scientists have a name for it. They call it the sonic pulse.
The sonic pulse. So if they're making a noise, why can't I hear it? I've been hiking my whole life. A tree has never, yelled at me.
Yeah, and it never will. The reason is all about frequency. It's the same reason you can't hear a dog whistle.
Ah, okay.
These sounds are ultrasonic. We're talking between 20 and 100 kilohertz.
And our hearing just stops. It tops out around 20 kilohertz, and that's if you're lucky.
Precisely. We are just biologically not tuned into this channel. But that doesn't mean the sound isn't there. I mean, this is the same range that bats and dolphins use to communicate.
So a bat flying over a forest on a dry day, it wouldn't hear silence.
Not at all. To a bat, that forest would sound like a really chaotic factory floor.
Wow. So we're just walking through this total cacophony, but we're deaf to it.
We're walking through a shouting match with perfect noise-canceling headphones on.
Okay, I have to know the how here. Because when I think of sound, I think of vocal cords, lungs pushing air, something rubbing together. A tree is just a solid block of wood.
Yeah.
How does it make a sound?
That's the perfect question. And to get the answer, you have to look at the tree's plumbing. You have to look at the xylem.
The xylem, right. That's the tissue that pulls water up from the roots to the leaves.
That's the one. Now, trees don't have a heart. They don't have a pump. So they don't push water up. They pull it. It's all based on suction, on negative pressure.
The classic straw analogy, right? Water evaporates from the leaves and it just sucks more water up from the bottom.
It is, but we need to upgrade the analogy to really get what's going on. So don't imagine a normal straw. Imagine you're trying to drink, say, an incredibly thick milkshake.
Right.
Through a straw that is as thin as a human hair, and it's 300 feet long.
You couldn't do it. The suction required would be, it's impossible.
It's immense. A tall tree is generating negative pressure that's equivalent to dozens of atmospheres. So inside those tiny xylem tubes, the water molecules are holding on to each other for dear life.
Cohesion, the hydrogen bonds.
Exactly. It stops being a liquid and starts acting more like a solid rope that's being stretched tighter and tighter.
Okay, so you have this rope of water, and it's under incredible tension.
Now, you add a drought, the soil gets dry, the roots can't find any new water, but the sun is still out, the leaves are still trying to pull.
So the tension just keeps going up.
It skyrockets until eventually, snap. The tension becomes too much for the water molecules to handle. The rope breaks.
And that's the sound, the water snapping.
That is the sound. The scientific term for it is cavitation. When that column of water breaks, it instantly flashes into a vapor bubble. And that tiny, tiny explosion sends a shockwave through the wood.
A pop.
A pop. That's the ultrasonic click that scientists record.
So the scream is literally the sound of the tree's insides failing. It's a sound of fractures.
It's the sound of hydraulic failure. Pop, And then another one, pop, pop.
That completely changes how I think about a thirsty plant. You know, you picture your houseplant just kind of drooping sadly. This is violent. The tree is literally ripping itself apart inside.
That's a perfect way to describe it. It's trembling with these little failures. And it's not just a few. In a big tree, during a bad drought, we're not talking about 1 or 2 clicks. We're talking thousands of cavitation events an hour.
Thousands per hour.
Yeah.
So if we could hear this, it wouldn't just be a pop. It would be more like a constant crackling.
A constant barrage of noise.
Oh, yeah, let's go there. Let's really try to imagine this. The source material had this great thought experiment. You're standing in a pine forest. It's a hot, dry afternoon.
Right. Picture it. It's late summer, hasn't rained in weeks, the air's totally still. To your ears, it's silent. Maybe you hear a bee, but that's about it. Total peace.
Okay, now I put on these special headphones that can hear ultrasonic frequencies and pitch them down for me. I flip the switch. What happens to my quiet forest?
The quiet is gone instantly. You'd just be hit with this wall of sound. The source called it a crackling, popping symphony of distress.
I think I read one scientist compared it to the sound of popping bubble wrap just everywhere all at once.
Or, and I find this one kind of ironic, like 1,000 microscopic champagne bottles being opened at the same time.
That is ironic. This is the opposite of a celebration.
It's a panic signal. And the craziest part is you'd be able to hear individual trees.
Oh, wow.
Yeah, you could walk through the forest with your eyes closed and diagnose it. You'd pass by a healthy cedar. Maybe it's got its roots in some deep water source. And from that tree, silence, maybe a single occasional pop.
But then a few feet away, there's a Douglas fir in some really dry soil.
And that tree is just going off. Click, click, pop, click, click. It's this rapid fire sound. You are literally listening to that organism fight for its life in real time.
An acoustic fingerprint of stress. It's just amazing to think that information has been broadcast for millions of years, and we've just been walking around thinking it was quiet.
We have been completely deaf observers. We wait until the leaves turn yellow to say a tree is sick, but by then, the internal damage has been happening for a long, long time.
Which brings me to the so what, you know? This is an incredible discovery, but is it just a cool fact, or can we actually use this for something?
Oh, it's huge. The application is already starting to change agriculture. High-tech farming, forestry. This is a game changer.
How?
Well, think about how we water crops now. It's pretty basic, right? A farmer goes out, checks the soil, maybe sees the plants are looking a little droopy.
Right, and then they turn on the water. It's all reactive.
Exactly. By the time the leaves are yellow, you've already lost growth. You've lost yield. The stress has already happened. But now, with this knowledge, they're developing tree stethoscopes.
You mean like actual microphones for plants?
That's basically what they are. Little sensors you clip right onto the trunk or the stem. They listen for that specific ultrasonic pop of cavitation.
So the plant itself tells you when it's thirsty.
Before you can see any damage at all. It's precision irrigation. You don't water on a schedule. You water when the plant says, hey, I'm starting to pop in here. I need a drink.
That seems like it would be critical for saving water, especially now.
It's absolutely vital. We can't afford to waste water, and this lets us give the plants exactly what they need when they need it, not a drop more.
And for forestry, I'm thinking about those massive forest die-offs we see from drought.
Same principle. These sensors could be an early warning system for an entire ecosystem. You could monitor a whole forest and hear when the collective stress level hits a dangerous point long before all the trees start turning brown.
It's literally giving a voice to the voiceless.
It is. It's bridging that huge communication gap.
You know, there's another part of this that I found even more fascinating, and that's the evolutionary question. You said biology rarely wastes anything.
It's a pretty solid rule, yeah. If a signal exists, someone's probably using it.
Okay, so if trees have been screaming in ultrasound for millions of years, who is listening? It just feels unlikely that this sound is just pointless.
And that is the absolute frontier of this research right now. We know certain animals can hear it, but the really compelling idea is about insects, pests specifically.
Like bark beetles.
Exactly. Bark beetles are devastating to forests, but they don't attack healthy trees. They can't. A healthy tree will just drown them in sap.
So they need to find a tree that's already weak, already stressed by drought.
Right. And the big question has always been, how does a tiny beetle find the one sick tree in a forest of thousands?
It hears the popping.
It's a very strong hypothesis. It's the dinner bell theory. They might be smelling chemical cues too, but it's very likely they're also hearing the cavitation clicks.
That is just It's terrifying. The tree is in distress, it's screaming for help, and that very scream is what attracts the predators that will kill it.
It's a horrible feedback loop.
But could it work the other way? For beneficial insects, like pollinator?
That's the other theory, yeah. A bee wants a flower with a lot of nectar, and making nectar takes a lot of water. A plant that's cavitating, that's clicking and popping,
It's not going to have much nectar.
probably not. So the sound might be a signal to the bee that says, don't waste your energy here, the bar is closed.
So the insects are navigating this invisible, or I guess inaudible, acoustic map of the forest's health.
It's entirely possible. And we've been walking through this whole time, completely unaware. We've been looking at the forest, but we haven't been listening to the right channel.
It makes you wonder what else is out there that we're missing.
It really does. It's just a profound reminder that our sensory world, the human world, is just one tiny slice of what's actually going on.
The deaf observer.
We are the deaf observer, yeah. We think we're getting the full picture, but we're missing most of the conversation.
There was a line in the source material. It said, "We aren't just missing the sound, we are missing the scream of the ecosystem." That really hits you.
It does. It kind of forces an empathy for something like a plant, which is usually hard to do. It's one thing to see a dry tree. It's another thing to know that it is physically trembling and crying out.
It reframes the whole relationship. It makes the suffering of an ecosystem feel more tangible.
And maybe that's the real takeaway here. More than the tech or the biology, it's just that shift in perspective, acknowledging that this world is so much more dynamic and so much more communicative than we ever thought.
You know, I'm actually going hiking this weekend, and normally I get to a quiet spot and I just sort of, appreciate the silence.
Oh, and now?
Now I think I'll be listening for it, wondering which trees are quiet and which ones are shouting.
You'll probably be glad you don't have the special headphones. Sometimes ignorance really is bliss.
That's a good point.
Yeah.
I'll stick with my illusion of silence, but yeah, with a lot more respect for what's really happening. The world is louder than we think. That covers 6. Ready for the next one. Let's head to fact 5. Welcome back. We are moving right along in our countdown. Let's dive into fact number 5.
We are indeed. And for this one, we're leaving the microscopic world we touched on and heading out to the American West. Specifically, we're going to Fish Lake National Forest in central Utah.
I have to say, looking at the photos, the setting is it's deceptively peaceful. Let me just set the scene for you. Imagine you're on a high-altitude slope, maybe around 9,000 feet. It's autumn. The air is crisp, the sky is that kind of piercing western blue, and you are just surrounded by this incredible grove of quaking aspens.
Populous tremuloids. Yeah, it's actually the most widely distributed tree species in all of North America.
Right, and they're called quaking for a very specific reason. Their leaf stem, the petiole, is that right?
The petiole, correct. It's flat, not round.
And that flatness acts like a pivot point.
Exactly. It's an aerodynamic trick. It lets the leaves flutter in even the slightest breeze, which reduces wind drag on the branches, but it also helps, light filter down to the lower leaves.
The technical side is fascinating, but the visual effect is just pure magic. It looks like thousands of little golden coins shimmering in the air. So you're standing there looking at what, for all the world, seems like a normal, healthy forest. 100 acres of these stark white trunks. But here's the twist. This is why we're talking about it. Your eyes are completely lying to you.
Oh, completely. They're deceiving you in the most fundamental way possible. Because what you're looking at, it's not a forest. It's not a community of different trees. It is a single, solitary, living organism. One individual.
That's the part that just takes a second to really sink in. We are not talking about a family of trees. We're talking about one thing, and it has a name that I think fits perfectly.
It does. It's known as pando.
Yeah.
It's Latin. And it translates to eye spread.
Eye spread. It sounds almost like something out of science fiction, doesn't it? But before we get into the crisis it's facing, and it really is facing a serious one, we need to unpack the biology. Because how can 47,000 trees be one tree? That just seems to defy the definition of what a tree is.
It challenges our definitions, absolutely. But to understand pando, you have to think about two specific biological terms, the ramette and the genet.
Okay, let's break those down.
A ramette is what you see above ground. It's the stem, the trunk, the branches. If you walk up to pando and hug one of the trees, you're hugging a ramette.
Okay.
But the genet is the entire genetic individual, the whole colony, including that massive, massive underground infrastructure.
So the 47,000 trunks, those are the ramettes. They're basically just branches that happen to pop out of the ground.
That is a perfect way to think about it.
Yeah.
They're genetically identical clones. If you took a DNA sample from a trunk at the very bottom of the hill and another one from a mile away at the top, they'd be an exact match.
And they match because they're physically connected. This isn't some, metaphor about nature being connected. This is plumbing.
It is literal hard infrastructure. If you could just, peer back the soil from that hillside, you wouldn't see separate root balls for each tree. You'd see one massive, tangled, singular root system.
I love that idea of painting the roots with a fluorescent dye. That really drives it home.
Right. Imagine you inject some glowing blue dye into just one of those aspen trunks. In a normal forest, that dye would just stay put. But in Pando, you would literally watch that blue light travel through a subterranean highway. It would just spread acre after acre. It's a shared reservoir.
Meaning they're sharing resources, water, nutrients?
Constantly. Water, nutrients, even chemical signals. So if the trees on the south side have plenty of water, they can theoretically send some of that water to the trees on the north side that are struggling. It's like a socialist utopia of trees.
Or a Borg collective.
Yeah, that's probably a fairer comparison, given all the cloning.
I found this one analogy in the research that I thought was pretty visceral. It's a little bit body horror, but it works.
Okay, let's hear it.
All right, so imagine you could just detach your fingers from your hand. You take your fingers and you bury them in your backyard.
Okay, that is immediately weird.
Stick with me. So from each of those buried fingers, a full-size copy of you grows out of the ground. Looks like you, talks like you, has your exact DNA.
But the catch is what's happening underground.
That's the catch. Beneath the dirt, all those copies are still connected to your original hand. They're all being fed by the same circulatory system, the same heart. So you have all these yous standing around looking like individuals, but they're all one being underneath. And just imagine doing that 47,000 times.
That's Pando. It is one being that has just multiplied its limbs on a colossal scale. And, that biological reality, it creates some incredibly eerie phenomena. Because they are one organism, they behave with a synchronicity you just don't see anywhere else.
Give me an example of that. How does that show up?
Phenology. That's the study of seasonal cycles in nature. So in a regular forest, different trees have different genetics, right? They wake up at slightly different times. One might leaf out early, another a week later. But with Pando, the signal is chemical, and it comes from that shared root system. So all 47,000 stems leaf out almost perfectly in sync.
That must be wild to see.
It's like a giant creature opening 47,000 eyes at the exact same moment. And in the fall, it's even more dramatic. The color chain sweeps across the hillside in this single, unified wave. It doesn't look like a patchwork quilt. It just shimmers all at once.
It really hammers home that idea of a single consciousness, or at least a single physiological engine driving the whole thing.
Precisely. It acts as a unit because it is a unit.
Okay, now I want to talk about scale, because when you realize it's one organism, the stats go from, impressive to just mind-boggling. Where does Pando actually sit in the record books?
It's one of those things that's heavily debated, but it's generally considered the heaviest living organism on Earth. By mass, anyway.
So heavier than a blue whale?
Oh, by a long shot.
Yeah.
We always think of the blue whale as the champion. A big one might weigh 200 tons. Pando is estimated to weigh around 6,000 metric tons.
So 30 blue whales.
30 blue whales all put together. It's just thousands of tons of biomass. And in terms of area, you're talking about something that covers more ground than 15 football fields.
But this is where I want to push back a little on the common facts about Pando. Because when you look at media coverage, you always see one number pop up for its age. 80,000 years old.
Yes, the 80,000-year-old forest.
Ooh.
It makes for a great headline.
But is it actually true? The scientists in our source material seem way more hesitant about that number. Why is that?
And you're right to be skeptical. That 80,000-year figure is a possibility, but it's, let's say, on the extreme end. The problem is, dating a clonal colony is incredibly difficult.
Why? Can't you just count the tree rings?
That's the trick. You can count the rings on a ramet, one of the trunks. But remember, the trunks are temporary. An individual aspen stem only lives for about, 100 to 130 years? Then it dies, falls over, and rots away.
So the historical record keeps getting deleted.
Exactly. The physical wood that was alive 5,000 years ago is just gone. It's soil now. The root system is what persists. But you can't really date roots with rings in the same way. So that 80,000-year number comes from climate models and growth rates, basically assuming Pando's been spreading since before the last ice age.
But there are other methods, right? I read about using molecular clocks.
Yes, and that gives us a much more conservative but still incredible estimate. By looking at genetic mutations that build up over time, basically counting the typos in the DNA, Recent studies suggest Pando is probably closer to 14,000 years old.
Okay, so maybe not 80,000, but 14,000 years is still just staggering. That means Pando sprouted right after the last ice age ended.
Correct. So whether it's 14,000 or 80,000, it's been on that hillside since long before the pyramids, before the Roman Empire, probably before written history even began, just sitting there, quietly cloning itself.
And the way it stays alive is this kind of immortality by committee.
In a way, yeah. Think about how a normal tree handles a disaster, like a fire. The tree burns and it dies. End of story. The genetics are lost.
But for Pando,
Pando just hides underground. When a fire burns down all 47,000 trunks, the root system is insulated by the soil. It just waits. And then that disturbance actually triggers it. It's a hormonal response to send up a massive flush of new shoots.
Wait, you mentioned a hormonal trigger. What was that? Auxin suppression.
Exactly. So the mature trees above ground produce a hormone called auxin, which basically tells the roots, hey, we're good up here, don't grow new stems. When a fire or a disease kills those trees, that auxin signal stops. The roots get the message, all clear to grow, and they launch thousands of new suckers.
So the destruction of the forest is the trigger for its rebirth.
It's a reboot. It replaces its old, damaged body with a fresh young one. It's like the ship of Theseus, but made out of wood. It replaces every single part of itself over time, but the organism, the pattern, it persists.
However, and this is where we have to shift gears, because this story takes a really dark turn. As amazing as this sounds, surviving ice ages, surviving fires, the research shows Pando is currently failing.
It is. And this is the part that keeps ecologists up at night. This eternal clone, this thing designed to live forever, is shrinking.
What could possibly hurt something that big? It survived mammoths, for crying out loud.
It's not one big event. It's a
No?
chronic condition. The biggest threat is actually pretty mundane, but it's devastatingly effective.
Browsing.
You mean being eaten?
Specifically being eaten by mule deer and cattle. You see, Pando's whole strategy relies on those new shoots. As the old trees die, the root system sends up young suckers to replace them. That's the cycle. But right now, those young shoots are essentially candy. And because the predator populations have changed, we don't have wolves or mountain lions patrolling that area anymore, the deer have nothing to fear.
Oh, this is the landscape of fear idea.
A classic concept in ecology. Yes. In a balanced ecosystem, herbivores are nervous, they take a bite, they look up, they move on. But without predators, the deer just stand there. They treat Pando like an all-you-can-eat salad bar.
So the babies are being eaten before they can grow up?
It is a total demographic collapse.
Yeah.
Imagine a city where there are plenty of 90-year-olds, but every time a baby is born, it just vanishes. Eventually, the city dies out. That is what's happening to Pando. The old generation is standing, but when they fall, there's no younger generation to take their place.
That is just terrifyingly simple. And humans are involved too, obviously. The cattle.
Yes, cattle grazing adds to the pressure. Plus, fire suppression. We've stopped the natural fires that used to trigger those huge regeneration events. So Pando's old, it's tired, and it's being eaten alive.
You know, there's a terrible irony here. Pando was alive when megafauna mastodons, giant sloths, were walking around North America.
It absolutely was. It watched them go extinct.
Exactly. It survived the extinction of the megafauna. It survived the rise of civilization. And now, it might be taken out by deer and cows because we messed up the predator-prey balance.
It's the ultimate irony. It survived the Ice Age. It might not survive the lack of wolves.
So what are we doing about it? I saw something about fencing.
There is intervention happening. The Forest Service and groups like the Friends of Pando are fencing off sections. The idea is just to block the deer and cattle long enough for a new generation of shoots to get tall enough, about 6 to 8 feet, where their main bud is out of reach.
And does it work?
It does. The photos are shocking. Inside the fence, you see this thick, healthy jungle of young aspen. Outside the fence, it's like a park, just grass and old trees. But, you know, we can't fence the whole world. It's a Band-Aid, not a cure.
This whole story just brings up some really heavy questions. We started this talking about biology, roots and clones. But when you look at Pando, it feels more philosophical.
That's what fascinates me most.
Yeah.
It poses this puzzle. What does it even mean to die if you're designed to be eternal?
Right, because death is usually binary. You're alive or you're dead. But Pando is just blurry.
It is. Is Pando a thing, a static object? Or is it more of a pattern? Because right now, it is simultaneously dying old trunks, are rotting and regenerating or trying to. It holds life and death in the same body at the same time.
It challenges our whole obsession with the individual. We like to think of ourselves as these separate, contained units, and Panda just says, no, I am a network.
Exactly. And I think there's a lesson there for how we view conservation. We tend to want to save things, save the whale, save the tiger. But with Panda, we have to save the process. The relationship between the roots, the shoots, the fire, the predators. If you break that process, the organism fails.
And the stakes are so high if Pando dies. If we let the last shoot get eaten and the root system finally runs out of gas, what have we actually lost?
Is it just 47,000 trees? We can always plant more trees. Or have we witnessed the death of a single ancient entity? A unique individual that's been a silent witness to history for thousands of years.
It puts so much weight on this one moment in time. We are just a blink of an eye in Pando's lifespan.
We are tourists in Pando's life.
And yet we're the ones holding the scissors.
Right.
The question is whether our generation will be the one that finally breaks that cycle. Are we the asteroid that finally takes Pando out?
Or will we be the reason it gets to live for another 10,000 years? That's the choice. And frankly, since we're the ones who broke the engine by removing the predators, we have a moral obligation to fix it.
It's a lot to think about the next time you see an aspen tree shivering in the wind. You might be looking at a tiny part of something so much bigger.
And much more fragile than it looks.
That covers 5 pounds.
Ready for the next one? Yeah. Let's head to fact 4. Welcome back. We are moving right along in our countdown. Let's dive into fact number 4.
Okay, and for this one, we really have to shift our perspective. We've been talking about these really fast processes, chemical signals, networks.
Right.
Fact 4 forces us to slow down, way, way down. We are talking about the heartbeat.
The heartbeat. And let's be super clear for everyone listening. You're not speaking metaphorically here.
No, not at all.
This isn't the heart of the forest in some poetic sense. You mean a literal physiological pulse?
That's exactly right. A
Yeah.
rhythmic, measurable, an actual expansion and contraction happening inside the tree.
Which just sounds, it sounds impossible given what we think we know about plants.
Yeah.
We see trees as, static.
Statues of wood, yeah.
Exactly. They react to things,
Yeah.
sure. They grow towards the sun. But a pulse that implies this constant cyclical movement, it sort of challenges the whole definition of a tree as a passive thing.
It absolutely does, and that's why this is such a big deal. We see them as, architecture, columns holding up leaves.
Door panels, basically.
Right. But the research we're looking at, specifically a study using terrestrial laser scanning, it shows that trees are in constant rhythmic motion. And this is independent of any wind.
Okay, let's start with the methodology.
Yeah.
Because if you tell me a tree has a pulse, my first question is, how do you know it isn't just the wind
Of course.
or the wood settling or something? How do you rule out all that noise?
That was the #1 hurdle for the researchers. To prove it, they had to create these incredibly specific conditions. They call them circadian nights.
Meaning what, exactly?
Meaning 0 wind, absolute stillness, and total darkness.
And the darkness is to rule out any immediate reactions to sunlight, photosynthesis and all that.
Exactly. They wanted to see what the tree does when it's supposed to be sleeping. And they didn't just point a camera at it. They used high-resolution terrestrial laser scanning.
Okay, so what does that actually involve?
Think of it as creating a point cloud. It's millions of tiny laser measurements that map the exact shape of the trunk and branches with, sub-millimeter precision.
So you're building a 3D model of the tree in real time and watching for any tiny changes.
Precisely. And what they found was this consistent, unmistakable movement. Trunks, branches, they were all shifting by millimeters, sometimes up to a centimeter, in a repeating cycle.
Wait, a centimeter? A centimeter of movement on a solid oak tree is... That's actually a huge amount.
It's significant, yeah.
Yeah.
If a concrete pillar in a building moved that much, you'd condemn it.
Right. And you mentioned humidity. Wood swells with moisture, doesn't it?
It does, but if it were just absorbing night air, you'd expect it to just swell, a linear expansion.
Or something chaotic.
Or chaotic, yeah. But that's not what they saw. They saw a pattern, a coordinated up and down cycle.
So it's not a sponge. It's a pump.
It looks an awful lot like a very, very sluggish heartbeat. One full beat, the expansion, the contraction. It takes a few hours, but it's rhythmic. And crucially, it's synchronized across the entire tree.
That synchronization part, that's the kicker.
It is.
That means it's not just some local thing happening. It implies a system-wide signal.
It implies the tree is acting as one single cohesive hydraulic unit.
I want to get to the how in a second, because the physics of lifting water hundreds of feet up is already mind-boggling. But first, help us visualize this. If I'm sitting next to a birch tree at 2 in the morning, what's happening?
Well, the first thing is you wouldn't feel it.
Right.
This is what some call the tempo trap. We're just too fast. If you put your hand on the bark, there's no thumping. The frequency is just way too low.
I'm not going to feel 60 beats per minute.
Not even close. But if you were looking at the laser data, the visualization, you'd see the trunk physically swelling outward. At about chest height, the diameter would increase by roughly 3 millimeters.
3 millimeters. So what, the thickness of a couple of pennies stacked together?
About that, yes. The tree is literally inflating. It's like a lung taking one very, very slow, deep breath in.
And then, as dawn approaches,
The whole process reverses. The trunk contracts, it shrinks back down, the lung exhales.
so what's the mechanism? What's driving this? Because, what we all learned in biology class was the cohesion tension theory.
Right, the giant straw model.
Yeah, the sun hits the leaves, water evaporates, and that suction just pulls more water up from the roots. It's all passive.
That's been the dogma for a long time. And look, that theory is still valid. It explains a lot of the water transport, especially during the day, but it treats the tree like a passive pipe.
Just a conduit.
Exactly. It assumes the tree doesn't have to spend any energy on this, but this heartbeat suggests there's an active component. The tree isn't just a straw, it's also a pump.
A pump.
Or, to use a really great analogy from the research, think of it as a skyscraper of straws.
You're talking about the xylem, the tubes that carry the water.
Yes. But imagine the walls of those straws aren't plastic. They're lined with living, active cells.
And these cells are doing something.
They're actively manipulating pressure. And this goes back to your point about synchronization. The theory is that these cells are creating a kind of peristalsis.
Wait, peristalsis. Like the muscle contractions in our intestines that move food along.
Functionally, it's a very similar idea. Obviously, plants don't have muscles, but these cells are actively pumping ions, potassium mostly, and sugars around.
Ah, so they're manipulating the osmotic gradient.
Bingo. Osmosis 101, right. Water follows the solutes. By pumping ions into the cells, they force water to rush in. That creates what's called turgor pressure,
And that pressure physically expands the cells.
which expands the trunk, and that pressure wave helps push the whole column of water upwards. Then they release the ions, the pressure drops, the trunk contracts, and the cycle begins again.
So it's not just being pulled from the top by the sun, it's also being pushed or squeezed from the bottom up.
It's a distributed pump. There's no single heart organ. The heart is the entire trunk. Every cell along that water column is part of the pump.
That solves a huge physics problem, doesn't it? Relying only on tension to pull water 300 feet up a redwood always seemed so fragile.
Very fragile.
One air bubble, one break in the column cavitation, and that whole section is dead. A pump adds a huge safety margin.
It does. It keeps the water column intact, but it comes at a cost. This isn't free solar energy anymore. The tree has to burn its own fuel sugars from photosynthesis to power these little ion pumps. It's actively spending energy to circulate its fluids.
Which makes it sound a lot more like an animal. It's burning calories to move its own blood.
In a sense, yes, and it's so incredibly slow. If you were a water molecule at the root, your journey to the leaf is measured in days, not hours.
Okay, but let's talk about the timing. You said it swells at night and shrinks during the day. That feels backwards. Shouldn't it be pumping hardest when it needs the most water during the day?
It's a great question, but you have to think about the whole water budget. During the day, transpiration is just going wild. The tree is losing water through its leaves way faster than it can pull it up from the ground.
So the whole system is under tension. The straw is collapsing a little.
Exactly. The stem actually shrinks because the water inside is being pulled so hard. But at night, the little pores on the leaves, the stomata, they close up. Transpiration stops.
And that's its chance to catch up, the recovery phase.
That's when the active pump really takes over. The tree rehydrates itself, it uses that turgor pressure to refill all its tissues and basically pressurize the system for the next day. The heartbeat is the tree having a long, slow drink all night long.
A nocturnal recharge cycle.
It is, and figuring this out has turned this from just a cool fact into a really critical environmental tool.
Okay, so let's talk about the practical side. If we can measure this heartbeat, I assume we can tell when the heart is struggling.
And that's the game changer for forestry, for anyone managing urban trees. We're now seeing what are basically tree stethoscopes being deployed.
Which are what? Dendrometers.
Automated dendrometers, yeah, which just measure the diameter with incredible precision, or continuous laser monitors. By watching the rhythm, the amplitude of this daily heartbeat, we can get a real-time EKG of the tree's health.
So if the heartbeat gets weaker, if the nightly swelling isn't as much,
Then you know it's running a water deficit. It didn't fully rehydrate overnight.
it's like the tree's version of an arrhythmia.
That's a perfect way to put it. It's a clear, early warning sign of hydraulic stress. And the key is that it's early. Usually, we don't know a tree's in drought until the leaves turn brown.
By which point it's often too late to do anything.
Exactly. The cellular damage is done. But the heartbeat changes weeks, sometimes months, before you see any visual signs. We can see the impact of a heat wave the day it happens.
I can see how that would be vital for fire prediction. If a whole forest's pulse is weak, you know it's a tinderbox, even if it still looks green.
Or for precision agriculture, or just for cities trying to save historic trees. You water them when their pulse tells you they're thirsty, not on a fixed schedule.
It changes the tree from a resource to a patient.
From an object to a subject. And that really brings us to the bigger philosophical idea here.
The what is life question.
Yeah. We have a very human-centric checklist for life, don't we? Does it move? Does it breathe? Does it have a heartbeat?
And on that checklist, trees always failed on movement and heartbeat.
Because we were judging them on our time scale. We live in a world of seconds and minutes. Trees operate in hours and decades. We just fell into the tempo trap.
It's a relativity problem.
It is.
To a mayfly that only lives for a day, we probably look like a static mountain.
That is a perfect analogy. And now we have the technology, the lasers and sensors that let us hear at their speed. And when we do, we realize they check all the boxes. They move, they pump fluid, they have a rhythm.
It really blurs that old hard line between plant and animal. We think of behavior as needing neurons, a brain. But this pumping, it requires coordination from the roots to the leaves.
It implies some kind of information processing that we just don't understand yet.
Which brings up that alien analogy from the source text.
Yeah.
It makes you wonder, what other life are we missing just because it operates on a frequency we can't perceive?
That's the haunting question, isn't it? When we look for life on other planets, we're looking for signals that look like ours. Fast radio bursts.
Right.
What if we find a planet where the dominant life form has one heartbeat a century, or communicates one thought over a millennium?
We'd classify it as geology. We'd land on it and start drilling, never knowing it was alive.
We would be completely deaf to it, just like we've been deaf to the pulse of our own forests for all of human history. We're only now building the hearing aids to listen to our own planet.
It suggests vitality isn't about speed. Maybe it's about persistence.
And trees are masters of persistence. They've been playing their music all along. We just weren't patient enough to listen.
So the big takeaway here isn't just a cool fact about trees. It's that the world around us is so much more active, so much more alive than our senses tell us.
We're walking through a crowd of pulsing, breathing beings every time we go to a park. We just have to remember their now is a lot longer than our now.
A crowd of slow-motion skyscrapers.
A crowd of slow-motion skyscrapers.
I think that's a pretty powerful place to leave it. We went from a few millimeters on a tree trunk all the way to searching for alien life.
It's a lot to take in.
It certainly is. That covers 4. Ready for the next one? Let's head to fact 3.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 3.
Okay, so this next one, this is a segment that I think it really fundamentally shifts how you perceive the air around you.
And we need to start this one with a sensory baseline. I want you to just picture that specific smell of a dense, old-growth forest. You know, that sharp, clean scent of pine needles, or the deep, earthy aroma of cedar.
It's so distinct, it fills the lungs in a way that city air just doesn't.
Right, and we usually just categorize that smell as, you know, pleasant or refreshing. It's an aesthetic thing.
Or a vacation thing.
Exactly. But the hook for fact number 3 is that this aroma isn't just a background texture. It is a complex chemical interaction.
It's essentially an invisible atmospheric pharmacy.
Yeah.
When you are in that environment, you're inhaling active medicine with every single breath.
That is the core of this deep dive.
Yeah.
Anti-cancer aerosols. We are looking at the premise that forest air is chemically engineered in a way that directly impacts our immune function. So let's strip away the poetry of fresh air for a moment and look at the actual chemistry. What exactly are we inhaling?
Well, scientifically, that forest smell is a collection of what are called volatile organic compounds, or phytoncides.
Phytoncides, okay.
Yes. The word literally means plant and killer. Trees and plants synthesize these compounds and they release them into the atmosphere.
So what are we talking about specifically? Like what molecules?
If we break it down, We are talking about specific molecules like alpha pine, which is what gives you that classic pine scent, or limon, which has that sort of citrusy wood note.
It really sounds like we're describing the ingredients of a high-end essential oil.
That's a very fair comparison because essential oils are just concentrated extracts of these very compounds.
Right.
But the critical point here, the thing you have to understand, is the intent. The tree isn't releasing these compounds for us. It's not trying to create a pleasant ambiance for hikers.
Nature is rarely altruistic in that way. There's almost always a survival function.
This is chemical warfare. I mean, think about it. Trees are stationary. They can't run from predators. They can't swat away pests.
So they have to fight where they stand.
Exactly. They've evolved this incredibly sophisticated chemical defense system. They synthesize these phytoncides to kill bacteria, to destroy fungi, to repel insects, and to prevent rot.
So the forest air is actually a defensive perimeter.
It's an antiseptic zone. Those invisible molecules you smell drifting from the cedar bark are actively hunting for microbes to destroy.
That reframes the entire experience for me. You know, we walk through a glade thinking it's so peaceful, but on a biological level, the air is thick with weapons.
Precisely. And this is where the biology gets really interesting for us. Because what acts as a weapon for the tree?
It acts as something else for us.
It acts as a signaling mechanism and really as medicine for the human body.
And this is where we move from just speculation, the general idea that nature is healing, into some really hard data. We're not just relying on folklore here.
Not at all.
Oh.
There's robust research, a lot of it coming out of Japan, regarding Shinrin-yoku, or forest bathing.
Shinrin-yoku, that's a term that sometimes gets dismissed in the West as a mystical, maybe?
It can, but the Japanese government actually incorporated it into their national public health program way back in the 80s.
Wow.
They treated it as clinical preventative medicine.
Mm-hmm.
Researchers conducted these extensive field studies where they monitored human physiology in forest environments.
And what did they find?
The breakthrough discovery wasn't just about, say, a lowered heart rate. It focused on a specific component of our immune system, the natural killer cells.
Natural killer cells. It's an aggressive name, but I guess it's accurate given what they do.
Well, it's very accurate. NK cells are like the immune system's special forces. Unlike other immune cells that need to be told what to look for, NK cells are constantly patrolling the body.
What are they looking for?
They're looking for cells that have gone rogue, specifically virus-infected cells, and crucially for this topic, tumor cells.
So these are our frontline defense against cancer development.
They absolutely are. And the studies showed a direct, powerful correlation. When subjects spent time in a forest environment, just inhaling these phytoncides, the count of NK cells in their blood increased significantly.
Just from breathing the air.
Just from the exposure. And it wasn't just the number of the cells, it was their lethality. Their activity levels spiked.
So they became more effective killers.
Much more. The research shows that forest visits elevate the intracellular levels of specific anti-cancer proteins.
You're talking about proteins like perforin, right?
Perforin is the key player here. The name really gives away its function. It perforates. When an NK cell finds a tumor cell, it releases perforin to literally punch holes in the target cell membrane.
It breaches the wall.
It opens the gate. And once those holes are drilled, the NK cell injects other enzymes called granzymes, which go into the tumor cell and trigger apoptosis.
Which is programmed cell death.
The cell self-destructs.
So practically speaking, the environment is passively arming your immune system. You walk through the woods and your body is stocking up on the ammunition it needs to terminate cancer cells.
That is the biological reality.
Mm.
And what's maybe most surprising is the durability of this effect. You might assume the boost just fades the moment you step back onto the pavement.
Right, like a sugar rush, it just wears off.
But the data suggests otherwise. The heightened NK cell activity, the increased protein levels, they can persist for more than 7 days after the forest visit ends.
A full week. That implies a cumulative effect then. A weekend trip isn't just a temporary pause, it's a systemic reset that offers protection for the following week.
Correct. But I know the question that's probably forming in the mind of a skeptic right now.
I can guess. How do we isolate the variable? You go to the forest, you're not checking emails, you're not in traffic. Isn't it possible that just simple stress reduction is boosting the immune system and the smell has nothing to do with it?
That is the most common and the most important critique. Is this chemistry, or is it just the placebo of relaxation?
So how did they test for that?
Well, the researchers designed a control experiment that I find absolutely fascinating. They removed the forest entirely.
They took the nature out of the equation.
Completely. They had subjects stay in standard hotel rooms in a city, No trees, no hiking, no nice views, just a bed and four walls.
Okay.
But while the subjects slept, the researchers used humidifiers to vaporize stem oil from hinoki cypress trees into the room.
So they just pumped the phytoncides directly into the sleeping environment?
They isolated the chemical compound. And the results. They were remarkably similar to the actual forest walks. The subjects in the hotel rooms showed significant increases in NK cell activity and those anti-cancer proteins.
Wow, so that really settles the mechanism debate. It's not just the psychology of being on vacation.
It's a physiological reaction to a specific chemical stimulus. It confirms that phytoncides are a primary driver. We're looking at a biological lock and key interaction.
Let's unpack that interaction a bit more. The source material uses a really helpful analogy, drawing a line between how this works versus how, say, a vaccine works.
It's a really important distinction. A vaccine is like an intelligence briefing. You introduce a harmless piece of a pathogen to train the immune system to recognize a specific enemy in the future.
It teaches the system what to fight.
Exactly. It's highly specific targeting. Phytoncides function differently. They don't provide intelligence on a specific target. Instead, they act as a general stimulant.
So if a vaccine is the dossier on an enemy,
Phytoncides are like upgrading the weaponry and the logistics for the entire army.
it's a force multiplier.
It is. It activates and enhances the defenders you already have. It wakes them up and makes sure they're fully loaded with perforin and granzymes. It doesn't tell them what to kill. It just makes them incredibly efficient at killing whatever shouldn't be there.
The evolutionary implications of this are just profound, because it forces you to ask why our bodies would be so responsive to chemicals produced by trees.
You have to look at the timeline of our species. For, 99.9% of human history? Where did we live?
We were embedded in the ecosystem.
We lived in the forest. We evolved in a constant chemical bath of phytoncides. Our respiratory systems, our immune systems, they all developed in an environment where these airborne antiseptics were just a constant variable.
So the body expects them. They're part of the baseline operating environment.
I think that's a perfect way to put it.
Yeah.
It suggests a co-evolutionary dependence. Our immune systems calibrated themselves relying on this external chemical support. We, in a way, outsourced a portion of our defense to the atmosphere.
And now, in the modern era, we've just drastically altered the parameters of that deal.
Drastically.
Yeah.
I mean, consider the modern context. We've migrated into concrete environments where the dominant aerosols are tire rubber particles, nitrous oxides, and industrial particulate matter.
We've replaced the medicine with toxins.
We have removed the chemical signaling our bodies evolved to expect. We are, in effect, fish trying to thrive in a tank where the water chemistry is fundamentally wrong. We can survive, sure, but we're operating at a deficit.
It's interesting you use the word deficit, because we often frame pollution as the addition of bad things. But this suggests the health crisis is also driven by the subtraction of the good things.
We've created an environment of depletion. And it's not just the immune boost we're missing. The source material also highlights that phytoncides lower cortisol and sympathetic nervous activity.
That's our fight or flight response.
Yeah, our stress response.
Yeah.
So the forest air is working on two fronts at once. It suppresses the stress hormones that weaken immunity while actively boosting the cells that fight disease.
It's a synergistic effect. And when you remove a human from that context, you lose that dual protection.
You do.
Which brings us to the application of this knowledge. We can't just dissolve our cities and go back to being hunter-gatherers, but this data really challenges how we approach urban planning.
It demands a complete reframing of the role of vegetation in our lives.
Currently, we view trees in a city as landscaping. You know, they're there for shade, or to break up the gray of the concrete. They're aesthetic.
Or we view them as carbon sinks, which is valid, of course.
Yeah.
But this chemistry suggests a tree is actually a piece of public health infrastructure.
A passive medical device.
It is a component of the atmospheric pharmacy. So when a city planner decides to cut down a row of trees to widen a road, they aren't just changing the look of the street. They're dismantling the infrastructure that helps regulate the immune systems of everyone living there.
That changes the entire argument for conservation. Preserving a forest isn't just about saving biodiversity for the animals.
No.
It's about maintaining the reservoir of compounds that keep us healthy.
And think about the potential for design. We talk about smart cities in terms of digital connectivity. But a truly biologically smart city would be designed to weave this chemical exposure into the daily grid.
So the commute itself could become the therapy.
Imagine if our walkways, our schoolyards, our office districts, Imagine if they were designed to ensure you are inhaling phytoncides as you go about your day. I mean, if a 3-day forest visit provides a week of boosted cancer defense, what would be the impact of daily low-level exposure?
That's the critical question. We spend billions on reactive healthcare, treating the cancer, treating the infection, and we're neglecting the preventative mechanism that nature provides for free.
It suggests that protecting nature is, at its core, a form of self-preservation. By protecting the forest, we are protecting the invisible shield that our own bodies rely on.
It all circles back to those natural killer cells. They're just sitting there like dormant mercenaries, waiting for a chemical signal that we have largely cut off.
We are starving them of that signal. We are observing a population suffering from a nature deficit that goes all the way down to the cellular level.
It leads to a fairly uncomfortable hypothesis to wrap this all up.
It does. We look at the rising rates of autoimmune disorders, cancers, general susceptibility to illness in the modern world. And while the causes are obviously complex,
Of course.
we have to ask the question, are we experiencing a kind of pandemic of weakened immunity simply because we have disconnected ourselves from the forest air?
Because we unplugged the life support.
We unplugged the external battery that charges our internal defense system. If the forest is an external extension of our immune system, which the data strongly suggests it is, then destroying that environment is akin to amputating a part of our own biology.
That is a heavy realization. But on the other hand, it also offers a very tangible solution. The remedy is literally growing out of the ground.
It is so accessible. Go for a walk, plant a pine tree, just breathe deep. It matters more than you think.
So the next time you catch that scent of pine or cedar, remember, you aren't just smelling the woods, you're recruiting allies.
A chemical alliance, millions of years in the making.
That covers 3. Ready for the next one? Let's head to fact 2.
Welcome back. We are moving right along in our countdown. Let's dive into fact number 2.
This one, you know, this specific fact is one of my absolute favorites in this series. It really forces us to completely rewire how we look at a forest.
Rewire how we look at a forest. That's a pretty big claim.
It is. It challenges the dictionary definition of individual, and honestly, it even challenges the definition of alive.
Okay, that's a serious buildup. I'm assuming we aren't talking about the usual stuff then, photosynthesis, carbon capture, that kind of thing.
No, we're going way deeper than that, literally. We are heading to the North Island of New Zealand. Imagine we're standing on a forested slope surrounded by these huge kauri trees.
Kauri trees, right? Those are the ancient ones, the giants.
The absolute giants. They just dominate the landscape, but we aren't looking at the giants today.
Okay, so you've set the scene. What are we looking at?
I want you to look down. Right near your feet, there's a stump. It's maybe 3 feet tall, a bit wider. It's weathered, gray, totally unremarkable.
Just a piece of dead wood.
Exactly. It's covered in moss. Maybe a few ferns are poking out of the bark. To the naked eye, it's just what's left over from a tree that fell or was cut down ages ago.
Yeah, I can picture it. It's the kind of thing you'd trip over and not even think twice about. It's dead.
Right. And, biologically, you have every single reason to think it's dead. It has no branches, it has no leaves, and this is the crucial part. Because it has no leaves, it has no chlorophyll.
Which means no photosynthesis.
Exactly. It's biology 101. Photosynthesis is how plants make their food. They use sunlight, turn it into sugar, and that fuels everything.
So if a tree loses all its green tissue, it can't eat.
It can't eat, it starves, and then it dies. That's the rule.
So by all the laws of nature, this stump should be decomposing. It should be, turning back into dirt.
It should be. But a couple of scientists, Sebastian Lusinger and Martin Bader, they were studying this forest and they noticed something odd. This stump just didn't look like it was rotting the way it should.
So they took a closer look.
They did. They set up instruments to measure gas exchange and water flow.
And what did they find?
They found that reports of its death were, greatly exaggerated. The stump was alive.
Alive? How?
Biologically active. The cambium, that's that thin layer of living tissue right under the bark, was green and healthy. And this is the kicker, sap was moving through it. The stump had a heartbeat.
Okay, hang on. Let's just pause and unpack that because it sounds physically impossible. You just said no photosynthesis.
No.
So if it's not making its own food, where is the energy coming from? It's like finding a car driving down the highway at 60 miles an hour, but you pop the hood and there's no engine.
That is a fantastic analogy. And if you see a car going 60 with no engine, what's the only possible explanation?
It's being towed.
Precisely. It's being towed. Or in this case, it's being fed.
Yeah.
The scientists realized this stump wasn't surviving on its own at all. It was being kept on life support by its neighbors.
With other kauri trees. The big ones.
Yep, the stump was plugged into the grid.
How? Are we talking about, like, a fungus network? I know mushrooms can connect trees sometimes.
That's usually the answer, the mycorrhizal networks, but in this case, it's even more direct. It's a phenomenon called root grafting.
Root grafting. I've heard of grafting, like in an orchard, where you splice a branch onto a different tree trunk. But this is happening naturally, underground.
All the time. I mean, think about a really dense forest. You have all these massive root systems just pushing through the same soil, fighting for space.
Right, they must cross over each other constantly.
They do. They rub against each other, the pressure builds, and eventually the bark wears away at that contact point. And then the vascular tissues, the actual plumbing of the trees, they fuse together.
So they literally solder their pipes together.
Literally. They become one single vascular system. So the water, the nutrients, the sugars flowing through the giant, healthy tree right next door can just cross that bridge and flow right into the root system of the stump.
That is wild. So the stump essentially hacked the system. It hardwired itself into its neighbors.
Or the neighbors hardwired into it. But here's where this deep dive gets really interesting. It's not just that they're connected. Lusinger and Bader tracked when the water was moving. They looked at the timing.
The schedule of the flow.
Exactly. And they discovered something we can call the night shift.
The night shift. I like the sound of that. What does it mean for a tree?
Well, to understand it, we have to look at what the healthy trees are doing during the day. The sun's up, it's hot. The big trees, they have millions of leaves up in the canopy, and they are photosynthesizing like crazy. To do that, they're transpiring.
Transpiring, that's basically plant sweat, right?
Basically, they open these tiny pores, the stomata, and water evaporates out. This creates this incredible suction, like a giant straw drawing water all the way up from the roots to the very top leaves.
So during the day, the big trees are just incredibly thirsty. They're hogging all the water pressure.
Correct. The flow is almost entirely vertical, straight up the big trunks. The stump, well, it has no leaves to create that suction, so it just can't compete. It's biologically invisible during the day.
But then the sun goes down.
The sun sets, photosynthesis stops, the pores close up, the transpiration halts. That massive upward pressure in the big trees just drops. The whole forest kind of relaxes.
And that's when the stump gets its turn.
That's when the physics completely shifts. The sensors showed this distinct, sudden spike in water movement into the stump, specifically at night. When the giants go to sleep, the pressure equalizes, and water and sugar flood across those root grafts into the area of lower pressure, which is the stump.
I'm just trying to visualize this. Like, you're standing in that New Zealand forest at 2 in the morning, it's pitch black, it's silent, but underneath your boots, there is this invisible rush of resources. It's like the stump is on a ventilator that only turns on when the rest of the hospital ward goes to sleep.
It's a haunting image, isn't it? The source material uses an analogy that I found, well, it's a bit dark, but it's incredibly accurate.
Oh, the neighbor analogy. Yeah, I remember reading that one.
Yes. Why don't you walk us through it?
Okay, so the article basically says, imagine you have a neighbor who died 10 years ago, but he's still in his house breathing. And the only reason he's breathing is because everyone else on the block hooked up IV lines through the shared sewage system to pump nutrients into his body.
It's so grotesque.
It is. It sounds like something out of a horror movie. But when you apply it to the trees, it's exactly what's happening. This isn't just sharing. This is keeping a corpse functional.
It is life support. Distinctly and undeniably. The stump has zero agency here. It cannot feed itself. It is entirely dependent on the charity, or at least the mechanics of the network.
Which brings us to the big question. The why? Because nature is usually pretty efficient, right? Evolution doesn't really favor wasting energy.
That's the central dogma, yes.
So why do it? I mean, sugar takes a ton of work to make. Water is precious. Why would these healthy, dominant Gowrie trees give away their hard-earned resources to a leafless, unproductive stump? It seems like a really bad investment.
That is the evolutionary paradox. If you look at this through a strict, survival of the fittest lens, the healthy trees should have just cut that stump off years ago, sealed the graft, kept the sugar for themselves.
Right. So why didn't they? Did the scientists have an answer?
They have theories, and this is where we have to expand our thinking, because the answer could be mechanical, or it could be something that changes how we define the organism itself. There are 3 main theories.
Okay, let's break them down. What's theory number 1?
Theory 1 is the big body theory. This is sort of the practical utilitarian argument. It suggests that the stump is being kept alive because it's still doing a job.
What job can a stump do?
Well, it doesn't have leaves, but it still has roots. Have to remember, this stump was probably a massive tree once. That means it has this wide spreading root system that goes deep into the soil.
Okay, I see where this is going. It's an anchor.
Exactly. Those roots are holding the hillside together. They're stabilizing the soil. If the neighbors just let the stump die completely, the roots will rot. If the roots rot, the soil loosens.
And if the soil loosens, you get erosion. Suddenly, the healthy trees are at risk of sliding down the hill in the next big storm.
Precisely. So under this big body theory, it's not charity, it's infrastructure maintenance. The healthy trees are paying a kind of sugar tax to maintain the very foundation of the forest floor.
That makes a lot of sense. It appeals to the logical part of my brain. I'll feed you, because if you go down, you might just take me with you.
It's a form of mutual assurance. But then you have the second theory, which is called the network lock.
Network lock sounds a bit more technical.
It's actually more mechanical. This theory suggests that the connection might just be an accident that the trees can't fix. Remember how we said the vascular tissues fuse together?
Yeah, the plumbing is soldered shut.
Well, trees don't necessarily have valves, they can just close off. Once those tissues are fused, the flow is just dictated by physics, pressure gradients, osmosis. There might not be a biological mechanism to say, okay, the trunk is gone now, cut the line.
So they're basically stuck with it.
Potentially. If a tree tried to seal off that connection, it might risk infection or damage its own root. So the flow just continues by default. It's not a choice, it's just the path of least resistance.
That's a bit more tragic. It's like a subscription you can't cancel.
Exactly. The gym membership theory of forestry. But then we get to the third theory, and this is the one that I think is the most profound, the superorganism theory.
I think I know where this is going, and I love it.
This theory proposes that the trees, they just don't recognize themselves as individuals at all. We look at a forest and we see tree A, tree B, tree C. We count the trunks. But the superorganism theory says that underground, those boundaries just don't exist.
So to the healthy tree, the stump isn't a neighbor. It's just part of me.
Yes. Think about your own body. You have parts of you that aren't exactly productive. Your earlobes, maybe? They consume blood, they require energy, but they aren't doing the heavy lifting like your heart or your brain.
But I don't cut off blood flow to my earlobe just because it's not writing a podcast script.
Exactly. You keep it alive because it's part of the whole. The superorganism theory suggests the forest acts as a single hydraulic entity. The resources just flow to wherever the pressure is lowest, like blood flowing to a healing wound.
That just blows my mind.
Yeah.
We are so obsessed with where I end and you begin. But this stump suggests that in a mature forest, that whole distinction is completely artificial.
It suggests that survival isn't a solo sport, and this is really where the biological facts start to turn into a philosophical mirror for us.
Yeah, let's get into that, because as I'm listening to all this, I'm thinking about how humans handle this stuff.
Yeah.
We are obsessed with independence.
We really are. In Western culture especially, the highest virtue is autonomy, being self-made, standing on your own 2 feet. If you're dependent, if you need a lifeline from someone, it's often framed as a failure.
Or at least a weakness. We have this idea that you have to contribute to be valuable. You have to, earn your keep.
Right. What have you done for me lately? But look at this stump. It contributes nothing visible. It doesn't photosynthesize. It only consumes resources. It is a botanical patient on permanent life support, to use the phrase from the research. And yet, the community keeps it alive.
It's a botanical social safety net.
It is.
Yeah.
And it works. The stump is still there. It's still growing, even if it's just microscopically. It's maintaining its cells.
It makes you question our whole definition of success. For a tree, we think success is being the tallest, catching the most sunlight.
That's the day shift definition of success. High competition, high output, climbing over your neighbors to get to the sun. And that is very human. We get that.
But the cowrie stump is the night shift definition.
Yes. The night shift is about redistribution. It's about the fact that when the pressure drops, the resources flow to the weak. It's about realizing that the longevity of the entire forest, the whole system, might depend on keeping the weakest parts alive.
Because you never know when you might need that anchor.
You never know. Today, you are the tall tree feeding the stump. Tomorrow, a storm could snap your crown off, and suddenly, you're the stump, relying on that same network.
That's a powerful way to look at it. It's not charity, it's resilience.
It's distributed risk. If everyone is connected, no one totally fails.
The source text had a line that really stuck with me. It said something like, "The stump isn't just refusing to die, it's testifying to a truth we've forgotten."
And that truth being that we are interconnected whether we like it or not.
It's funny, we treat the word freeloader as such a dirty word. But in a superorganism, there's no such thing. There are just different parts of the body in different states of health.
Right. You wouldn't call a healing broken bone a freeloader just because it's taking extra energy to knit back together. You give it the energy because you need the bone.
So if you're listening to this and you're feeling a bit like a stump, maybe you're not photosynthesizing right now, not at your peak, just remember the cowrie tree.
Yes, there's a place for the stump. There's value in just holding your ground, keeping the soil stable, and letting the network carry you for the night shift.
And on the flip side, if you're a tall tree right now,
If you're a tall tree, remember your resources aren't just for you, and sharing them might be the very thing that keeps the ground under your own feet from sliding away.
graft your roots. That should be the slogan.
It's a little horticultural for a bumper sticker, maybe, but I like the sentiment.
We'll work on the branding. But seriously, this deep dive really changes how I'll walk through the woods next time. I always look up, I look at the canopy, the leaves.
We all do. We're drawn to the light.
But now I'm going to be looking down. I'll be thinking about the whole conversation happening under my boots.
And it is a literal conversation. Chemical signals, water flow, electrical impulses. The wood wide web is kind of a cliche term now, but it's real. We are walking on the roof of a bustling subterranean civilization.
And in that civilization, even the dead, or the mostly dead, have a seat at the table.
The undead, the zombie socialist stumps of New Zealand.
I love that. The Zombie Socialist Stumps sounds like a great name for a punk band.
I would buy that album.
But it really is a hopeful story, isn't it? We started with what seemed like a rotting block of wood, and we ended up with a lesson on community resilience.
That's the beauty of looking closely. Fact number 2 wasn't just about a tree, it was about how life survives the hard times.
By holding on to each other.
By holding on tight.
Well, I think that is a beautiful place to put a pin in fact. Number 2. We've learned about hydraulic redistribution, the night shift, and we've learned that being a stump isn't the end of the world.
It's just a different phase of life.
That covers 2. Ready for the next one? Let's get to fact 1. We have finally reached it. The most magnificent revelation on our list. Fact number 1.
It feels heavy, doesn't it? We've been building to this moment for what, 9 deep dives now?
We have. And for anyone who's been on this extraordinary journey with us, we're not just, listing trivia.
No, not at all.
We're basically rewriting the definition of what a tree even is. We started this series thinking of trees as just wood and leaves, and we're ending it well.
Well, let's not spoil the reveal just yet.
Right.
But you're right, the previous 9 facts changed how we see trees as individuals, or maybe as communities. Fact number 1, this changes how we see the entire planet.
Okay, but before we get to the main event, I think we have to look back. We need to recap the journey. Because fact 1 only really makes sense if you remember just how wild things have already gotten.
I agree. It's worth doing a quick kind of rapid-fire recap. Think of it like the previously on segment of some really complex drama series.
Let's do it. Okay, so facts 10 and 9. For me, this part of the journey was the death of the individual. The idea that trees are just these loners in the forest, completely destroyed.
Right. We entered what you could call the socialist forest. Fact 10 was the wood wide web.
The fungal internet.
The fungal internet, yeah. We learned that the forest floor isn't just dirt, it's a circuit board. You've got this mycelium, these tiny fungal threads linking all the roots together.
And the stat that still gets me, a single teaspoon of soil can hold miles of these threads. Miles.
Which then sets up fact 9, the mother tree.
The matriarchs.
Exactly. These aren't just old trees, they are hubs. They recognize their own kin and send carbon nutrients to little saplings that are struggling. It's a social safety net that's been running for hundreds of millions of years.
So, okay, they have a society. Then the series got a little weird. It turned into a spy thriller.
The chemical and acoustic world? I like that.
Facts 8, 6, and 3. This is where we found out they're not silent, they're not passive.
No. Fact 8, the African acacia. A giraffe starts munching on it, and it immediately starts pumping out ethylene gas. It's a warning.
It warns its neighbors, and they start pumping toxins into their leaves. It's this distributed intelligence, but with no brain.
And if that wasn't creepy enough,
Oh, fact 6, the sonic pulse. This one still keeps me up at night.
the screaming trees.
Yeah, we found out that when trees are thirsty, they scream. But not, in a way we can hear.
It's ultrasound. It's something called cavitation. The water column inside the trunk gets so tight it just snaps, and it makes this little click, this pop. A forest in a drought would be deafening if we could hear it.
So the forest isn't silent, we're just deaf.
We're just deaf to it.
And then the flip side of that horror show was fact 3, the pharmacy arc.
The anti-cancer aerosols.
Right.
Trees defending themselves with these essential oils, phytoncides, that just by accident happen to supercharge our own immune cells when we walk in the woods.
Forest bathing. It's real medicine.
Uh-huh. Then we moved into the tree's body, facts 7 and 4. We found out they have a memory of thirst.
Epigenetics. This one floored me. They don't have a brain, but they learn. They remember past droughts by changing how their genes are expressed.
And fact 4, the heartbeat. This one's a bit controversial, but the evidence is fascinating. Trees don't just passively suck up water.
Like a straw.
Right. Their trunks actually expand and contract. They pulse. It's a very slow heartbeat, maybe once every few hours, but it's there. They're pumping.
Which brings us to the absolute edge of what seems possible. Facts 5 and 2. Defying death.
Sando. Fact 5, the eternal clone.
One tree that's also a forest of 47,000 stems. It's, what, 80,000 years old?
Potentially. It's effectively immortal. And then your favorite.
My favorite, yeah. Fact 2. The stump that refused to die. That kauri stump in New Zealand.
No leaves, no way to make its own food. It should be dead.
But it wasn't. Its neighbors were keeping it alive, pumping it full of water and sugar through their grafted roots. Like a community keeping an elder on life support.
The ultimate social safety net.
So, okay, trees talk. They scream, they have heartbeats, they learn, they refuse to let each other die. That is an insane resume. And you're telling me fact 1 tops all of that.
I am. Because every single thing we just mentioned, as amazing as it is a local phenomenon. It's about one tree, its neighbor, its grove.
Right.
Fact number 1 is different. Fact number 1 operates on a global scale. We're leaving biology behind, and we are entering planetary engineering.
All right, let's do it. What is fact number 1?
Fact number 1 is this. Trees do not just respond to the weather.
Oh,
They create it. They are the atmospheric architects.
atmospheric architects. Wow, that sounds like a job title from a sci-fi movie.
It basically is. We think of it backwards. We think, rain falls, the tree drinks it, it grows, the tree's passive. But the science shows the arrow points the other way. The trees are building the rain.
I mean, how is that even possible? Are we talking about something more than just, providing shade?
Oh, much, much more. It all starts with a process called transpiration. Now, I know everyone's heard that word in high school biology.
Yeah, plant sweating. That's what I remember. Am I close?
You're close, but sweating kind of undersells the sheer power of it. Sweating sounds passive, like a leak. This is an engine, a high-pressure hydraulic engine.
Okay, an engine. What do you mean?
Well, think about it. Water is heavy. Lifting it hundreds of feet against gravity it takes massive force. You can't suck water up a 100-foot straw. The physics just doesn't work.
Right, you pass out.
Exactly. So trees use the physics of evaporation to create suction. As one water molecule evaporates from a little pore on a leaf of stoma, it pulls on the molecule behind it, and that one pulls on the next one all the way down, like a taut, continuous rope of water from the leaf to the tiniest root tip.
So the whole tree is under tension. It's physically pulling.
It's under negative pressure.
Yeah.
And when you multiply that by millions of leaves, you're not just, dampening the air. You are injecting water into the atmosphere with force.
Okay, give me a visual for that.
All right. Imagine you are standing under a huge, mature oak tree on a hot summer day. You look up, it looks perfectly still.
Peaceful.
Peaceful, right. Now imagine you could see water vapor, like it was smoke. If you put on those magic glasses, that tree would look like it was on fire.
On fire.
It would be billowing these massive plumes of moisture upwards, just jetting them into the sky.
Wow. Okay, so how much are we talking about?
A single mature oak tree can lift and release about 40,000 gallons of water a year.
40,000.
Which works out to around 100 gallons every single day.
100 gallons?
Yeah.
From one tree?
Okay.
That's like filling up a bathtub and just dumping it straight into the sky.
Every day.
Every single day, exactly. Now, take that image of one oak tree and zoom out. Zoom way, way out to the Amazon rainforest.
Okay. The big leagues.
We call the Amazon the lungs of the earth, but it's really more like the heart of the global water cycle. Get this. The Amazon rainforest transpires around 20 billion tons of water per day.
20 billion with a B.
With a B. And to put that in perspective, that is more water than the Amazon River itself pours into the ocean. And stop, I need to process that. The Amazon River it's the biggest river on the planet. It's like an ocean flowing through a continent. And you're telling me the invisible river in the sky above it is bigger.
It is. The river on the ground discharges about 17 billion tons a day. The trees pump 20 billion tons into the air.
It redefines the map for me. You look at a map, you see the blue line, and you think, there's a river. But the real river is the ghost river overhead.
Scientists have a name for it. They call them flying rivers. And just like a river on the ground, this flying river flows. It travels thousands of miles, hits the Andes Mountains, and then gets pushed south.
So, wait. The trees in the Amazon are literally watering the farms in, say, Argentina.
Precisely. That moisture creates the rain for huge agricultural regions thousands of miles away. It's a continental water pump. And if you cut down the forest, you're not just losing biodiversity, you are turning off the tap for millions of people.
That's terrifying. It means the forest is infrastructure.
It is critical infrastructure,
Yeah.
but it gets even crazier. There's another layer to this. It's not just that they're moving the water, they're actively manufacturing the clouds.
Manufacturing them. How do you manufacture a cloud?
You remember the chemical warfare fact?
Hmm.
The terpenes and other chemicals trees release?
The stuff that smells like pine.
The very same. Well, when those chemicals rise up into the atmosphere, they oxidize and form these microscopic particles, and those particles become cloud condensation nuclei.
Okay, let's break that down. Cloud condensation nuclei. What does that mean?
Think of it this way. You can have air that is totally saturated with water vapor, 100% humidity, and still have no cloud and no rain.
Because it's still a gas.
Exactly. For that water vapor to turn back into a liquid droplet, which is what a cloud is, it needs a surface to land on. It needs a little seed.
It can't just stick to another water molecule.
It's really hard for it to do that and needs a nucleus. Usually in the atmosphere, that's a speck of dust or soot or sea salt.
Or the particles from the trees.
Or the particles from the trees. They are releasing the water, and they are releasing the seeds for that water to cling to. They provide the bricks and the mortar to build the cloud.
That is a full surface operation.
It is. And research shows that these tree-made aerosols actually change the clouds. They create more numerous, smaller droplets, which makes the clouds brighter.
And brighter clouds reflect more sunlight.
Right. Cooling the planet. So they're making their own rain and their own air conditioning.
That just completely flips the script. I always thought, it rains a lot, so a rainforest grows there.
But it's actually a rainforest grows there, so it rains a lot.
Yeah.
It's a feedback loop. The forest draws in water, it releases the vapor and the seeds, that makes rain, and the rain feeds the forest. It's a self-sustaining engine.
Which is incredible, but it's also scary because engines can break.
And that's the danger. If you deforest an area past a certain tipping point, you break the pump. The flying rivers dry up, the cloud seeds disappear, and the rain stops falling. Not just over the dead forest, but for everyone downwind.
We usually talk about deforestation in terms of carbon, save the trees to stop climate change. But this is about plumbing. The planet's plumbing.
That's a great way to put it. We see a drought. We call it an act of God or just bad luck. But often, that drought is a direct mechanical consequence of us removing the biotic pump the trees. We are taking a sledgehammer to the planet's water mains.
It makes that single oak tree in the town square look very different. It's not a decoration.
It's not. It's a piece of critical infrastructure. It's a biological machine working every day, lifting 100 gallons of water to keep our climate stable.
So we think of ourselves as the engineers of the planet. We build dams, we seed clouds. But fact one is telling us we're just amateurs compared to the trees.
That's the humility in all of this. We absolutely depend on the rain the trees build. We can't do what they do. Not on that scale, only the forests can.
It makes conservation feel less like a charity project and more like essential maintenance.
Exactly. If the water main to your city broke, it would be an emergency. You'd fix it immediately. That's what deforestation is.
And that's the weight of fact number one. They are the atmospheric architects. Without them, the sky we depend on just stops working right.
And when you put that together with the other 9 facts, the communication, the memory, the community, you realize we're sharing the planet with a quiet, stationary civilization that is profoundly important to our survival.
It's funny. We started this whole extraordinary journey looking at microscopic fungal threads under the ground.
Liquid Wide Web.
And we ended it with flying rivers that cross entire continents.
From the soil to the sky, it shows you, doesn't it? It's all connected. You can't just cut down one tree without shaking that whole web.
I think that's the perfect place to leave it. We just want to say thank you for sticking with us through this whole deep dive. It really changes how you look at a walk in the park, doesn't it?
It really does. And if this has sparked anything for you, don't let it stop here. Next time you see a tree, really look at it. Don't just see wood. See the pump, see the cloud maker, see the neighbor.
And keep an eye on this feed for our next series. We've got some more big topics coming up that are just as mind-bending, so make sure you're subscribed.
You won't want to miss it.
Thanks for listening to the Extraordinary 10 podcast.